Hello InfoPerson, this is Anton, and today we're going to be discovering something else from the closest star system to us. It looks like, after all these years, we've discovered another planet there. The star system that's gravitationally attached to the Alpha Centauri binary star system, and a system that made news a few years ago when a very interesting, potentially Earth-like planet was discovered in the habitable zone of Proxima Centauri, seems to contain another object. One of the least massive planets we've discovered so far. And so let's discuss this discovery in a little bit more detail, focusing on how it was found, and what this also means for the system as a whole, and for our understanding of the red dwarfs. And that's a somewhat important reminder. This particular star, unlike our Sun, is a red dwarf, which sort of has a few implications. For example, red dwarfs are known to be a lot more active in terms of flares and in terms of various geomagnetic storms. They also generally have a much longer lifespan, so there are a lot of differences between this particular star and what we have in the solar system. But they also represent the majority of the stars in the galaxy, and most of the terrestrial planets that seem to resemble Earth in at least density have actually been found around red dwarfs, at least to date. And so these particular star systems have actually become extremely important for our understanding of how terrestrial planets might develop in other systems, and if life might exist somewhere else. But up until 2016, this particular star system was not particularly interesting, simply because of the discovery of a terrestrial world not so different from planet Earth, at least in terms of the mass and the size, and also the fact that it was located in what's known as the habitable zone, where there is a chance for possibly liquid water to exist. Since then, several studies have been done on the system, and overall the scientists now believe that there is actually a very low chance for this particular system to potentially possess habitable conditions on the surface, or for this planet that is. Chances are it's actually receiving way too much radiation and way too many flares to maintain relatively stable atmosphere and liquid water. But obviously you never know. Because of this is the system that many scientists have been sort of proposing over the years to potentially use as the first target for interstellar probes that could reach the star system within possibly up to about 50 years if we propel them to extremely high velocities, in this case using lasers, and to then maybe report back. But that particular mission is still in its planning stages, and we don't really know if the so-called Breakthrough Starshot project is ever going to happen. But then in 2020 there was a sign of potentially yet another planet in the system, this time some sort of a gas giant, or possibly an ice giant, with the orbit that would put this planet relatively far away from the star, overall making it extremely cold and very likely completely uninhabitable. And this was discovered by using what's known as espresso, a type of a spectrograph that essentially looks at slight variations in frequency of light and is able to usually tell when something is slightly red-shifted or blue-shifted. And that's because in this case, this is how the scientists were able to discover this particular planet. As the planet orbits around the star, it basically starts pulling at the star, and this pull is then sort of visible in different red shifts and blue shifts of the starlight. Now, it's not actually pulling at it that much like in this image, unless the planet is extremely massive, but the actual variation becomes periodic and also becomes visible if you have a powerful enough instrument like espresso. As a matter of fact, this instrument is able to determine the variations in the orbit of the star itself, even if it's only moving by just a few meters across every single orbit. For example, not so long ago for our own Sun, a very similar approach was able to determine the exact center of our solar system with an overall error being less than 100 meters. And so this is already pretty accurate, but these particular instruments looking at distant stars can do so with even more accuracy to determine if there's something in their orbit. And so while finding that second planet, the Proxima Centauri C planet, they've actually noticed that there was something else going on, possibly another planet. We briefly discussed this in the video from a few years ago. Now, it wasn't really confirmed back then, and it sort of almost looked like possible noise, but the additional observations and additional calculations from the last few years determined that, well, it seems to have not been noise after all. There seems to be another terrestrial planet orbiting much closer to the star, with an average orbit here taking just over 5 days. And because of the proximity to the star, it also means that the temperature here is most likely relatively hot, at least 90 degrees Celsius or possibly around 200 Fahrenheit. so this is most likely not a potential source of life. But it is nevertheless a pretty interesting planet. And it also is, in terms of size at least, and in terms of mass, one of the smallest exoplanets ever discovered. So first of all, here's where it orbits compared to Proxima b, the first discovered planet. And assuming that it still has some sort of an atmosphere, it might resemble something like this. Basically, some kind of a terrestrial desert world. Slightly smaller than planet Earth, but also at the same time a lot less massive. Which means that its density is much lower as well, potentially even less density here than planet Mars. Although at this point, this is still a candidate planet, and so any properties we might be aware of right now could still change in the future with future observations. And so the most exciting part of the discovery here is actually the way that this planet was found. Once again through radial velocity, but in this case by observing tiny changes of approximately 40 centimeters per second that were showing us the changes in the velocity of the central star, Proxima Centauri, and being able to see 40 centimeter per second changes at a distance of over 4 light years away from us is kind of mind-blowing. It means that this particular technique has matured so much now that we're probably going to be discovering way more planets in the next few years, potentially even turning radial velocity method into the main method used to find exoplanets. And it would sort of make sense because for the transit method, the method that's used by most telescopes to find planets today, you really expect the planet to pass in front of the star. The chance that the star and the planet are aligned with planet Earth is not very high. And so in this case, radial velocity is the method that can actually find planets independent of the orbital orientation. So it's definitely the method that a lot of scientists are trying to develop and the method that scientists are trying to perfect in order to find more of these objects out there. And since this particular planet is also one of the least massive planets discovered to date, and also the smallest planet ever discovered using this particular method, by itself, this discovery is already a pretty big achievement for the astronomical community. As a matter of fact, planets that are less massive than planet Earth are generally pretty difficult to find. There's only a handful of them out there. As a matter of fact, there's like 30 or so, with the least massive planet ever discovered being just a little bit more massive than the Moon and also being one of the first planets ever found. This was a planet currently referred to as Draugr, and it's a planet that was discovered several decades ago by looking at the slight variations in the pulsations of a distant neutron star. With the overall system, despite being the first ever found, being the most unique as well. No other system has been found that seems to possess these unusual objects. More about this in one of the older videos somewhere right there or in the description. But anyway, we'll talk more about this and some of the other incredible discoveries in some of the future videos. For now, I guess it's super exciting to hear that the nearest star to us seems to have 3 planets. Possibly more. And that's of course the exciting part. As these methods become better and better, and as scientists develop new techniques, we will be discovering more of these unusual planets, or possibly very usual planets, orbiting in some of the nearest stars to us. Which means that, well, it's time for us to also find a way to get to those stars. Interstellar travel should be the next priority. For now though, we don't really have a good way to get there just yet. Because of the advances in various telescopes and because of various new surveys out there, the scientists have been actually making so many groundbreaking discoveries in just the last few years. And many of these discoveries are coming from our neighborhood, right here from the Milky Way, not so far from planet Earth. It's always been there, it's always been visible to us, but up until recently, we didn't really know what we were looking at. And in this video, we're going to be discussing this new discovery of 2 intriguing white dwarfs, relatively close to planet Earth once again, that have been recently discovered to possess very unusual properties, but more intriguingly, seem to possess signs of the oldest planets we've discovered to date, the oldest planets at least in the Milky Way galaxy. Hello info person, this is Anton, and so today we're going to be discussing this relatively new study that as always you can find in the description below, that use some of the most recent observations from the Gaia telescope, from the Dark Energy Survey, and from the European Southern Observatory, combining them into one study that makes these 2 white dwarfs, at the moment, some of the most exciting white dwarfs we've ever discovered. But before we talk about the discovery, a brief review about what these white dwarfs represent. This is essentially the future of the solar system. We know that around 97% of all of the stars in the Milky Way at some point are going to become white dwarfs, and that's of course including our own sun. but they're probably going to take slightly different paths, and not all of them are going to produce what's known as planetary nebula. Our Sun though, and a lot of other similar stars that are even more massive, up to about 10 solar masses in total, are going to eventually get really old, start producing a lot of winds and start to expand even more, and eventually leave behind a shell we usually refer to as a planetary nebula. There are quite a lot of beautiful ones out there we've discussed in previous videos. But right in the middle, there's going to be a leftover. The core of the star, also known as the white dwarf. The object that's extremely dense, only about the size of planet Earth, but usually possessing up to 1.4 solar masses in total, with the nearby Sirius B being the closest neighbor we have that has quite a lot of mass and is a white dwarf orbiting a partner known as Sirius A. This beautiful picture from Hubble telescope right here shows us both of these objects, and you can see that the white dwarf is actually really tiny in comparison. But as I mentioned, quite a lot of stars, including more massive stars, are going to become these objects. And some stars that have up to about 10 solar masses are going to go through their stages really quickly, possibly in just a few 100 million years, and turn into white dwarfs extremely fast as well. And so some of the oldest stars in the universe have already become white dwarfs that have been in existence for a pretty long time. Now the scientists have already discovered thousands and thousands of white dwarfs out there, but some of them seem to be really strange. Okay, white dwarfs are already pretty strange. I mean, by itself, this is really unusual matter, known as degenerate matter, that's essentially a kind of an ocean of electrons. But these two recently discovered white dwarfs are particularly strange. First of all, they were actually some of the coolest white dwarfs we've discovered. Coolest as in temperature cool. They were about 3000 Kelvin, which is much lower than a typical white dwarf, and is actually much lower than the Sun. In this case, the temperature is a lot closer to a typical red dwarf. But more intriguingly was actually the color that they were producing. One of them was somewhat blue, but one of them was somewhat red. And it's this unusual coloration and the temperature that hinted at something weird going on around these objects. And so the scientists decided to analyze them using spectroscopy by using ESO's, or European Southern Observatory's X-Shooter instrument that's able to produce super accurate spectroscopic observations. A typical image looks something like this. It's actually kind of beautiful. But what's important here is that it then shows us what sort of elements contained inside the light, coming from various stars or from various objects, allowing us to determine the composition of most objects we're looking at. And so in this case, they analyzed both of these objects, discovering that first of all, they were quite different, but more importantly, both of them were basically polluted white dwarfs. Polluted in the sense that they were both absorbing a lot of matter, a lot of gas, a lot of different materials, very likely with a large accretion disk like you see right here, with all of this then mixing on the surface and then directly affecting the atmospheric composition of the white dwarf. Yeah, the white dwarfs, they also have a bit of an atmosphere. But normally this atmosphere is pure helium, but in this case it wasn't. In one of the white dwarfs, it was a mixture of helium, sodium, calcium, lithium, potassium, and potentially something else, including carbon, which turned the white dwarf more red. And all of this stuff, very likely, almost certainly, came from the old planetary system that most likely survived the times when the star turned into a red giant and absorbed a lot of the other planets, which is probably what's going to happen to planet Earth sometime in the future. But as these planets survived, they slowly moved closer, and at some point the white dwarf possibly shredded them and started to absorb them onto its surface. But because in this case it was discovered that this white dwarf is approximately 10.7 billion years old, it means that these were the oldest planets in the Milky Way discovered so far. Okay, I guess not actual planets, more like planetary leftovers, but they were very likely planets up until recently, until the white dwarf shredded them apart and turned them into some kind of a disk. And the elemental presence around this white dwarf suggests that these planets were probably very different from anything we have in the solar system, which does kind of make sense because we believe that early planets were probably much different. Back then the universe was still kind of low in a lot of heavier metals and a lot of heavier materials, and for the most part had quite a lot of hydrogen, helium, lithium, and lighter materials, which of course implies that these planets were probably very different from anything we have here in the solar system, or actually in any of the other star systems that are much younger. Now we obviously have no idea what these planets would look like, or if they were terrestrial, if they had surfaces, or if they were just unusual gas giants, but they were clearly there, and the signs of them now being absorbed are also there as well. Chances are further investigations and analysis of this particular star is going to reveal more and potentially even discover what these planets were like. Since this is only about 90 light years away from us, it's one of the closest objects to us, it's going to be quite possible with modern instruments. But then there's also the question of the second white dwarf, the one that's not red, the one that's a little bit more blue. It's slightly farther away at approximately 120 light years away from us, and it's also a little bit younger at maybe just over 9 billion years to maybe almost 10 billion years old, but it's clearly also polluted, very likely absorbing planets as well. But in this case, the pollution is very different. Here, the analysis of spectroscopy determined that these planets were extremely Earth-like in terms of the debris that was depositing on top of the white dwarf. It actually kind of resembled Earth's continental crust. And that of course makes it super exciting and somewhat unusual. It does imply that maybe back then, Earth-like planets did exist as well, even though technically we kind of think that planets were probably much different. And so it's really the observations of the unusual mixture of helium with a lot of other elements that the scientists so far were able to work out that these were definitely planets, and one of them, or maybe even several of them, were potentially terrestrial and maybe even Earth-like. But also, with all of this disappearing nearly 10 billion years ago, which of course implies that these planets, if they did exist, could not have existed for more than about 3 billion years. And really at this point, anything else is just going to be speculation. Any kind of life, any kind of terrestrial conditions, none of this we can answer yet. But because 97% of all of the stars in the Milky Way galaxy are going to at some point become this, by performing more analysis and by performing more observations, at some point the scientists might actually come up with various models for what sort of planets create what sort of pollution on different types of white dwarfs in different regions of the Milky Way, allowing us to maybe one day reconstruct some of these planets in terms of models and obviously find out what sort of composition and what sort of properties they must have had. But just the fact that these planets existed 10 billion years ago, with Earth itself only being 4.5 billion years, is already pretty incredible, and also provides important evidence for the existence of planets early on and for the existence of planets most likely everywhere in the Milky Way galaxy, but also existence of Earth-like planets around stars that are not so different from our own sun. Well, actually a little bit more massive, but not so different otherwise. Although that's not really entirely true for that red white dwarf, the one that's closer to us. Here the planets are a little bit more mysterious. Because of the presence of lithium and potassium, and actually huge amounts of those elements, if this is coming from planets, and it probably is coming from planets, it's unknown what sort of planets they were. It would be completely different from anything we have in the solar system or anything we can even imagine. Now, one explanation here could be that it's coming from brown dwarfs, or a brown dwarf that used to exist here, but that's just a speculation, no proof just yet. Brown dwarfs are known to possess quite a lot of lithium. But I'm sure we'll be hearing more about this white dwarf, this particular white dwarf that's about 90 light years away from us, because it does seem to be a little bit different from anything we've seen. It's also extremely magnetic, super red compared to anything else, and the oldest white dwarf we've discovered so far with the lowest temperature, and also obviously planets. Hello wonderful person, this is Anton, and today we're going to be tackling a pretty interesting and a somewhat intriguing question that was recently asked in one of the studies you can find in the description below. Can a planet have its own mind? Can a planet be conscious? And though it's not a question that's going to be very easy to answer, it is nevertheless an extremely important question for the reasons raised in this particular paper. But because this is such a complex topic, we do have quite a lot to cover here. And I guess the first thing I wanted to talk about is the idea of mind itself. First of all, we still have no idea what intelligence, consciousness, or the idea of having a mind even is. In other words, self-awareness is not really that well defined. But for this particular paper, we're going to stick to one definition. It's the idea behind self-awareness having an ability to somehow self-maintain. So, for example, when you're hungry, your body finds a way to get you more food. When you're thirsty, it finds you more water. If something is not functioning well, it finds a way to try to fix it. So this self-maintaining is going to be sort of the basis for the principle of a planet having a mind. And that's because the idea of self-awareness is a very complex topic. And I'm only going to cover just a tiny part of this because there's going to be a future video discussing this in more detail. Actually, if you'd like to learn more about this, I'm leaving some of the links in the description, but one of the most common ways of testing if, for example, an animal is self-aware is what's known as a mirror test. And just as the name implies, it's a test involving a mirror. Pretty easy test to try at home if you have a pet or something. I actually tried this with my dog and unfortunately he failed. And the way it works is really simple. Let's just say we're talking about this baboon right here. You place a tiny visible dot somewhere on its face or maybe somewhere on its body, and then let this baboon interact with a mirror. If they start acting like this is another animal, the animal failed the test. However, if they realize that not only is that this is them, but they also start to look at the dot and try to remove it by essentially looking at the mirror itself, this would imply that the animal or whatever you're testing is self-aware after all. Here's actually a really good example of an actual test conducted with magpies, and we know that they are self-aware because they constantly try to remove a dot no matter what species of magpies this is tested on. So in this particular case, this is a self-aware species. Same has been done with several types of dolphins, whales, and a lot of different primates, and they also seem to be self-aware as well. But some animals, like for example dogs, tend to be somewhat self-aware. Some dogs pass the test, some don't. Actually, most dogs seem to not pass it, mostly because dogs are just not visual creatures. They tend to use their noses more, and they do pass the nose self-awareness test. Actually, there is an experiment that tested that as well. And so if you do have a pet at home, try it out for fun to see if your pet is also self-aware. But even this process, in terms of the actual brain function, is still poorly understood. There are certain brain parts that have been identified that seem to be responsible for self-awareness in us, in humans, but we're still really far from being able to exactly pinpoint where all of this is happening. More about this in one of the future videos. And that's because today we really want to talk about planets. Can a planet be self-aware? And the way that this argument starts is with the idea of the biosphere, with this beautiful image from NASA making a pretty good visual analogy. In some sense, biosphere could be seen as something that is alive. As a matter of fact, the so-called Gaia hypothesis that was proposed a few decades ago does kind of explore this in more detail, but most scientists today don't really think biosphere is alive like a typical organism, but they do think that the biosphere is a kind of a metaphor for an actual living being. Because here, depending on the conditions, everything sort of self-regulates. We have different organisms interacting with inorganic surroundings on the planet, and through these complex interactions of different types of organisms on the planet, the biosphere itself creates the ultimate conditions for life to stay on the planet for billions of years. And there are so many different analogies about how this works that can be visible pretty much everywhere. For example, at some point, plants started to produce oxygen by using photosynthesis. This then created a lot of other conditions necessary for other life to thrive. And over time it created different really large communities, such as for example forests, where everything becomes self-regulated. So in this case, we know that different types of forests can actually regulate everything in the forest by using the very extensive root system. So let's just say one of the trees somewhere is starving or needs a lot of nutrients, the entire system is actually going to send required nutrients to that particular tree. And these types of self-regulations and these types of activities where a lot of organisms sort of collaborate and cooperate is extremely widespread on our planet. And that's the idea behind biosphere. It's a creation of a kind of a self-maintaining system by the activity of all sorts of life on the planet. Something that naturally existed here for at least 3.5 billion years. But then we have this new introduction, us, and we tend to do our own thing. And specifically, we started to introduce a lot of other things that are slowly throwing the biosphere a little bit out of balance. So yes, there is pollution, there are a lot of other influences we create on the planet that tend to sort of change things, but in this case, it could be not a bad thing at all. As a matter of fact, this is kind of what the scientists in this paper are implying. They're implying that this is part of the evolution of the planetary system, and there's a next stage after this. So what exactly is this paper about? So first of all, the scientists in this paper suggest that there are 4 stages for all planets before they reach their ultimate stage. The most common stage for pretty much all planets we've discovered so far is the so-called immature biosphere. Something that was probably around on early Earth billions of years ago, with maybe just a little bit of microbes and bacteria on the surface, possibly some activity that could be detectable in the atmosphere, such as the production of CO2 and methane, but practically no self-regulation and no feedback of any kind. Stuff here exists, it does its own thing, but nothing is affected on the planet. And then suddenly we reach the second stage, the mature biosphere. And this is the Earth between about 2.5 billion years ago and approximately 540 million years ago. We suddenly have vegetation, we have photosynthesis, we have a lot of oxygen being circulated on the planet, suddenly we have things like ozone layer, and the biosphere becomes active and starts to maintain the habitability of the planet. Now this is something we are hoping to find somewhere out there. Chances are we might be able to find this if this is a common activity. And in this case, you're going to start seeing some other gases like, for example, oxygen. And then we have the current stage, the immature technosphere. We now have at least one species on the planet producing stuff that produces other stuff. And that species on the surface found a way to essentially use resources from the biosphere and from possibly the planet itself to create its own way to communicate, to transport things, to produce all sorts of different materials. But during that stage, because this is a completely new thing to the planet, it sort of throws it off balance and starts to introduce new materials. In this example, we have the so-called CFCs, the materials that we often associate with the ozone hole or with being extremely powerful greenhouse gases, with some other gases also changing their balance in the system. But the problem in this case, and the reason why it's called immature technosphere, is because it's not integrated in the biosphere itself. It's not integrated in the self-maintenance of the system. It adds a lot of new things, but a lot of those new things are either not doing anything or are actually making things a little bit worse. But more importantly, it's not regulated, and it's not regulated by the biosphere. And so in some sense, this actually starts working against the other parts of the biosphere. And that's unfortunately where we are right now. But then there's the next stage that the scientists propose, and the stage we should be aiming at. And as you can probably imagine, they refer to this as mature technosphere. The ultimate aim for the biosphere and for any technologically active species living on the planet. All of the systems in place, including all of the technology, is now somehow benefiting the entire planet, with all of the energy extracted from the planet not really harming anything and actually balancing out with everything else. But more importantly, in this particular case, this technosphere now also becomes part of the biosphere. It actually starts to sort of cooperate and enhance it even more. And it is precisely at this stage that the scientists behind this paper are making an assumption that the planet becomes sort of self-aware. Well, not self-aware like we are, but basically it's able to self-maintain. It sort of acquires a mind of its own, with all of the technological emissions being balanced out by other parts of the technosphere itself, with the entire technosphere working for the benefits of the planet and thus allowing the planet to exist for billions of years more. Naturally, not something we're doing right now just yet. As a matter of fact, one of the more brilliant quotes from the paper is that, well, there is definitely intelligence on the planet, but the planet itself right now is not intelligent yet. The planet does not have planetary intelligence. It doesn't have its own mind. But here the implication is that, well, maybe somewhere out there, we might actually already see certain planets that potentially possess this mature technosphere where the entire system is integrated into the biosphere and everything is able to self-regulate. And by having a complex system with a lot of interaction on the inside, this is when we start seeing a lot of different emerging properties. And in some sense, that's exactly what happens in our brains. All of these different connections between neurons start to create us. They create the intelligence. And so in this case, the scientists believe that, well, maybe something like this can potentially happen to a planet where intelligent species develops this particular technosphere, the next evolutionary stage of a typical planet. And so just like a biosphere that was able to maintain the planet for billions of years, the next stage, technosphere, can make it even better. Although I guess one question that's going to be very difficult to answer in this case is, okay, but how do we actually get there? And how would that look like if we were to look for this using telescopes? None of those questions are currently answerable, but it is definitely something we have to try to figure out. I mean, more or less for the existence of our own species. And so one of the main purposes behind this research is to really try to figure out where exactly should we be headed, what should we be doing in order to preserve the technosphere and to make it into something that to some extent acquires its own mind. With the other implication potentially also answering the so-called Fermi paradox. If we ever find some kind of a technological civilization out there, it's probably because they found a way to reach the stage. They didn't kill themselves, reaching an actual stage of planetary intelligence. And if we'd like to survive as well, for as long as possible, we definitely have to try to use our own intelligence for the benefit of the planet as a whole. But I guess baby steps. So pretty intriguing research, very interesting study, but something we'll discuss more in some of the future videos as well. Now today we still are not entirely certain if life exists somewhere else out there except for planet Earth. But one of the ways scientists are trying to figure this out is by trying to establish how life started here on planet Earth, and then by seeing if similar conditions could be discovered somewhere else out there on some other alien planet or some other alien object somewhere in the universe. And if one day we do discover an object somewhere that does seem to have very similar conditions to early planet Earth, this would imply that life could have started somewhere else out there as well. But even though the scientists have already discovered thousands of different exoplanets out there, not a single one of them seems to resemble planet Earth, and for the most part all of them seem to be really extreme. But it doesn't mean that similar conditions to early planet Earth could not exist elsewhere despite these planets being so different. Hello wonderful person, this is Anton, and today we're going to be discussing this new study that you can find in the description below that discusses these unusual planets that could exist somewhere out there that despite being extremely different from anything we have in the solar system could still have very similar conditions to early planet Earth and even possess liquid water for billions and billions of years, long enough for life to develop and to even evolve into something more complex, with the liquid water in this case being the most important component. Mostly because today we believe all of the early life very likely started in early oceans on planet Earth. Oceans that were very likely extremely different from anything we have today. Something we've discussed on the channel many times, and you can find some of these videos in the description below. But the main point in this paper is that we really shouldn't focus so much on various planets in habitable zones of their star systems. There could be some planets out there, very extreme planets that look nothing like this at all, that could easily maintain liquid water without the conditions that we currently have on planet Earth. And this paper goes into a lot of detail specifying at least one type of a planet that can easily sustain liquid water without looking like Earth at all. A somewhat dark, gas-like planet on the outskirts of the star system, or possibly even a planet we usually refer to as a rogue planet. A planet that does not orbit anything. It sort of travels across the galaxy completely by itself. Because it could have been created by itself, or it could have been ejected from an early star system before it changed too dramatically. With the main idea here being really simple. In order for liquid water to exist on any planet, you essentially need to have just the right temperature and just the right pressure. It doesn't have to be exactly the same as planet Earth, but it does have to fall somewhere in the green zone on this phase diagram of water. So for example, any planet with very low pressure is only going to have very limited opportunity for liquid water to exist. But a planet with a lot of pressure actually has quite a lot of different temperature ranges for where liquid water is possible. Although there is obviously a limit to this pressure, which is also visible in this diagram. And so if this is right here on planet Earth, you could technically have a planet with 10,000 times more pressure where liquid water could exist whether the planet was too cold or too hot. In other words, pressure here would actually determine quite a lot. And certain gases would also contribute to the greenhouse effect, thus increasing the temperature overall. We also know that early Earth, 4 to 4.5 billion years ago, was very different from how it is today, both in terms of the atmosphere and the presence of the liquid water on the surface. And more specifically, the atmosphere here was a lot more enriched in things like hydrogen and potentially even helium. And obviously a lot of other things coming from various volcanic eruptions and multiple collisions that were happening very frequently early on in the solar system. And so this very unusual primordial atmosphere that existed for several hundred million years very likely helped the liquid oceans to develop on the planet. But over time, all of this was stripped from the planet, with hydrogen and helium escaping into the outer space, with only heavier gases staying behind and eventually creating the atmosphere we know today. But we also know that larger planets, like for example Jupiter, Saturn, Neptune and Uranus, can easily maintain these hydrogen and helium atmospheres for much longer, despite the presence of the radiation from the Sun. Whereas some other planets, for example planets farther away from the star system, or rogue planets that don't even have a star, can actually maintain these hydrogen and helium conditions because nothing is there to strip it away from them. And so in theory, these planets could easily sustain this atmosphere and could actually exist in a very similar state, not for millions, but for billions of years, assuming that nothing star-like approaches too close to strip the atmosphere. And so based on this assumption, the scientists behind the recent paper decided to model several different types of planets and try to simulate what would happen to them over a period of billions of years, taking into account a lot of different things such as the pressure from the atmosphere, the intensity of radiation coming from the potential star, and more importantly, the amount of internal heat generated by the planet itself that would then serve as the main contributor to all of the heat needed for the liquid water to exist. And that's actually the important part, because even though here on Earth, the geothermal energy only represents a fraction of all of the energy we're receiving as a planet from everywhere, most of the energy does come from the sun itself. On these other planets, planets such as rogue planets or planets far away from their stars with primordial atmospheres, the internal heat would mean so much more. It would actually add up a tremendous amount of energy into the planetary atmosphere, with all of this energy trapped by the atmosphere itself. Suggesting, of course, that any kind of a geothermal heat, assuming that it stays on the planet, would actually be more than enough to maintain a liquid ocean on the planet for billions of years. With some planets in their calculations and their models maintaining these liquid oceans for tens of billions of years. Potentially much longer than even planet Earth. We know that on planet Earth, the liquid oceans are going to start disappearing once the sun becomes bright enough, and specifically about 10% brighter than it is today, with all this extra UV radiation stripping the atmosphere and then stripping the oceans as well. All of this will very likely happen in about 1.1 billion years from today. And so, at least in theory, these unusual worlds have a potential to sustain liquid oceans much longer than planet Earth. And in their calculations, they also found out that any super-Earth, which we know are very common everywhere in the galaxy, with a mass of about 1 to 10 masses of planet Earth, can easily maintain the liquid ocean somewhere on the surface, assuming that it orbits about 2 astronomical units away from the star or more, or if it has no star at all. But they do require a lot of atmosphere, a lot of pressure, hundreds of times more than planet Earth. But it's very possible for these planets to have these thick atmospheres, assuming that nothing disturbed them over time, and assuming that no star has ever had a chance to strip anything here, with the hydrogen and helium staying on the surface. And interestingly enough, not so long ago, the scientists have actually discovered some kind of an unusual rogue planet, very similar in mass to planet Earth, that was discovered accidentally using the so-called gravitational lensing effect. You can find out more about this somewhere right there or in the description below. Now, in theory, this could be one of these planets with liquid oceans. And it's even been suggested before that if some kind of an extraterrestrial intelligence wanted to find a way to travel across the galaxy without expending too much energy, it could actually do so successfully by trying to colonize these very unusual rogue planet worlds, and by then basically living on them or possibly sustaining themselves on them for millions and billions of years until these worlds come close enough to another star system. In other words, using them as a kind of a free transportation method. And so in that sense, both rogue planets and these unusual super-Earths farther away from their stars currently do represent a very interesting target in our search for potential life somewhere out there that's not planet Earth. Or at least for finding some kind of a liquid ocean planet somewhere out there. Now, until we actually find one, all of this is very theoretical, actually very hypothetical. All of this is based on modeling, and all of this is based on our modern understanding of how we think liquid oceans form on planets. But we only have one example to work with, planet Earth. And in terms of that one example, things here are extremely different from everything else we've discovered so far. Anything from the actual minerals our planet is made from, to the fact that we have a very specific moon of a very specific size that was created completely by accident during a planetary collision, to a lot of other details we've discussed in some of the previous videos, including the types of planets present in the solar system. So in that sense, we don't really know if these planets exist, but in theory, they could. And once we discover something else about them, I'll make sure to follow this up with another video. Hello wonderful person, this is Anton, and today we're going to be talking about a potentially really exciting discovery of what seems to be the first ever circumtriple planet. But what exactly is circumtriple? And why is this such a strange and unusual discovery? So let's discuss this in a little bit more detail, starting with the idea of exoplanets we've discovered so far. So as of today, we've discovered several thousand different exoplanets. The vast majority of these exoplanets were discovered by the very proliferous Kepler telescope. But in most cases, all of these planets usually orbit a single star, with most of these star systems looking something like this. But when it comes to the majority of the stars in a galaxy, in the Milky Way, we know that approximately 50% or actually over 50% of all of the stars are binary. Kind of like what you see right here. This is the nearby Alpha Centauri. Although a few years ago it was renamed into Rigel Kentaurus, so this is Rigel Kentaurus A and Rigel Kentaurus B. And many of the exoplanets have been discovered around these binary systems as well, usually orbiting one of the stars. But there's a type of an exoplanet that's extremely exciting and somewhat unusual, something that the scientists very often have trouble explaining. It's known as the circumbinary planet. A planet that orbits not one of these stars, but both of the stars at the same time. In the last few years, quite a few of these circumbinary planets have been discovered already, but why exactly is it that it's so difficult for these planets to exist? Well, it's really in regards to the orbital interaction between the stars. In binary systems, because of the gravitational interaction between the stars, they tend to create quite a lot of gravitational instabilities in the entire system. Now, a single planet can still exist around one of these stars, especially if they're really far away from one another, but in order to have a planet orbiting both of these stars, previous mathematical analysis has established that there's actually just a very specific area where a certain planet can successfully exist in a somewhat permanent orbit. But even in those areas, their orbital parameters would actually change with time. And so this is what we refer to as the circumbinary planet, sometimes also referred to as the Tatooine planet. Basically named after that scene from Star Wars where Luke Skywalker gets to see two stars in the skies of Tatooine. And in the last few years, NASA has already investigated several of these Tatooine planets and discovered that some of them can even be habitable and potentially have liquid water on the surface. And so a lot of the recent studies in regards to circumbinary planets have actually discovered that despite improbability and unlikeliness of these planets being possible, it seems that the universe has successfully created several of these planets that have already been detected in the last few years. But what about other stars? We know that about 20% of all of the stars in the galaxy contain 3 or more stars in the system. And a few years ago, the scientists have discovered the planet you see right here, known as Koi 5ab, which was the first exoplanet discovered in a triple star system. But as you can see from this diagram, the planet itself was orbiting only one of the stars, with the two stars here forming a binary, and then this binary forming another binary with a partner known as Koi 5c. Although here I need to clarify something. When we talk about multiple star systems, in pretty much every single case, in order for these multiple star systems to exist, they actually have to create binaries within binaries. So for example, a typical quadruple star system like this one right here will have two binaries orbiting around one another. In a quintuple or 5-star system, you'll usually have some sort of other formation involving a lot of binaries. And that's actually the only way that the stable multiple star systems can form. They still have to form binary systems. But one of the more intriguing and more interesting questions here is, but can a planet exist in orbit around 3, 4, or 5 stars? In other words, can we actually have not just circumbinary planets, but circumtriple, circumquadruple, or maybe even circumquintuple systems with a planet orbiting around several stars at the same time in a somewhat stable configuration? Well, looks like we might have found just one of these planets. So back in 1949, the astronomers identified this unusual system known as GW Orionis. The system was unusual simply because of the emissions it had. Today we know that this is what's known as the T Tauri star, which are normally extremely young stars, less than 10 million years old, that are going to develop into actual star systems in the next few million years. Now normally these are extremely active, they have a lot of different types of emissions, but they also usually have relatively large circumstellar disks. But about 10 years ago, the observations from GW Orionis established that the disks here were actually really different, they were extremely unusual. So even though they might not look very unusual from this side, further investigations established that there are 3 different disks and they're sort of more or less misaligned. And they're also extremely large. The distance from the star to the edge of the final disk is about 400 astronomical units, roughly around 10 times the distance of Pluto to the Sun. Although to be more exact, this here ends at about 46 AU, the second ring ends at 188, whereas the last ring reaches to a distance of about 338 astronomical units on average. Moreover, the disks also seem to be misaligned by about 137 degrees, with each of these disks also being relatively massive. This one contains about 74 masses of planet Earth, the second one contains about 168, and the last one contains about 245 masses of planet Earth, which will eventually turn into planets. And so the initial simulations from a few years ago established that a lot of this misalignment is very likely due to the interaction between the triple star system that's being formed right at the center. It sort of looks like this, like you see in the simulation from the European Southern Observatory. And so the unusual inclination of the disks here is very likely due to the star activity in the center, which makes this system one of the most gravitationally complex star systems that has ever been analyzed by the scientists. But the natural question is, can planets exist here? And more specifically, can actual planets form in the disks and remain there for billions of years? Well, unfortunately, there's no actual answer to this just yet, only speculations based on the analysis from this paper. And this is mostly due to the distances involved. This system is pretty far away, 1300 light years away from us, so unfortunately the scientists are unable to see actual planets in orbit here. But the recent study was able to confirm a very unusual speculation that seems to suggest that there is a planet here after all. They've confirmed that there is a substantial gap between the protoplanetary disks. The gap that would be very difficult to explain unless there was a planet forming there right now. And this is something that scientists have learned from a lot of other systems. Normally when you find some sort of a large gap between disks, that's because a lot of the mass here was absorbed by some sort of a massive planet that's being formed, turning into a gas giant. But in the past, some of the studies have also suggested that this unusual gap formation could have maybe formed by the complex interaction of the three stars. And since we know so little about these complex systems and the gravitational interaction with them, and because of the complexity of gravitational interaction of stars, and also because of the complexity of triple star systems, in theory it would be possible to create some sort of a disk misalignment and some sort of a gap in the disk. But the recent study decided to simulate this using a lot of complex computer simulations and a lot of three-dimensional hydrodynamic simulations to establish that the gravitational forces created by the stars would not be sufficient to create something that we're observing in the system. On the other hand, their simulations show that a presence of a planet here would definitely create something that we're seeing, with the massive Jupiter-like planet very likely just being hidden somewhere in the gap between the two disks. And if the scientists in this paper are correct, and if some of the future telescopes are able to actually see this planet, it would obviously imply that we finally found the first ever circum-triple planet, and at the moment the actual math behind this is pretty solid. It does look like this unusual system known as GW Orionis potentially contains one of the first such planets somewhere around 100 astronomical units away from the center of the system, which means that the universe has actually found a way to create a lot more unusual planets, the ones we thought would never really exist to begin with. And hopefully some of the future telescopes will be able to directly image this particular star system and directly detect this planet using some of the modern techniques. Nevertheless, a lot of these planets in multiple star systems are still kind of rare. To date, we've only discovered approximately 30 or so planets around a triple star system, and today it's believed that maybe about 2% of all of the multiple star systems will have some sort of a planet around them. But what exactly these planets look like, and what sort of conditions they have on the surface, and more importantly if any of them can actually be habitable, is a question we cannot really answer right now. They're still very mysterious, they're still extremely poorly understood, and until future studies we're not really going to know what happens around these unusual objects. For all we know, maybe the conditions here change so fast that they can never really be stable. And so this is something that we'll probably discuss in some of the future videos once more studies come out and once we find something else unusual somewhere out there. Hello InfoPerson, this is Anton, and today we're going to be talking about this star system right here that doesn't actually seem like anything special, but turns out it is. And turns out it's one of the strangest star systems we've discovered so far. And it's not because of this unusual cometary object you see right there. That's just a planet being evaporated because it's just way too close to the star. The strangeness of the star system comes from this recent discovery that suggests that one of the planets orbits in an extremely unusual way. It has a very strange polar orbit, something that's never been seen before in such a way, with the orbits sort of being like this. So let's discuss this in a little bit more detail, including potential explanations for how such a star system could be formed, and more importantly, how all of this was discovered and what this means for astronomy. But first of all, let's talk about the idea of orbits to begin with. So first of all, by studying a lot of different protoplanetary disks and a lot of early stars out there, the scientists in the last few decades have confirmed that the majority of star systems end up forming what's known as the protoplanetary disk, with the vast majority then leading to what we have in the solar system, a flattened disk with planets orbiting in a relatively similar plane of orbits. And the actual process of formation is pretty well understood. It's basically because of the conservation of angular momentum that forces a lot of things orbiting in a spherical shape to eventually flatten out and to eventually form a disk. This is something that's been simulated many different times using various computer simulations. And after this, all of these flattened disks eventually start forming coalescing shapes, which then turn into planets, with the vast majority of planets having relatively similar inclination. Now this is the case for the solar system, and it's the case for a lot of other star systems discovered so far. One of the best examples is of course TRAPPIST-1 system. The 7 planets of the TRAPPIST-1 are pretty much in the exactly same inclination, which is exactly why it was possible to see all of them orbiting in front of the star. This is basically how all of them were discovered. But naturally, you could still have some inclination differences here and there. And generally, the farther away from the star, the more inclination the object is going to experience, most likely due to the effects from a lot of other objects outside of the solar system. But in this case, it's still kind of difficult to imagine a star system where instead of having the same plane of orbit, at least one of the planets seems to be in a completely different polar orbit. So sort of like what you see right here, an orbit that's basically perpendicular to the rest of the star system. And turns out that this is exactly what the scientists have recently uncovered. And this is not a new star system either. It's been known to us for quite a long time. It's a star system that scientists believed looked like this, with 3 confirmed planets relatively close to the parent star. Now this is a K-type star, so it's actually a little bit smaller and a little bit less bright than our own Sun, but in every other respect it was an extremely average-looking system with 3 average-looking planets. A somewhat hot sub-Neptune right here that seems to be evaporating and slowly stripped away of its atmosphere because of the proximity to the star, another relatively hot sub-Neptune slightly farther away, and yet another sub-Neptune slightly farther away still. But one of these sub-Neptunes has an extreme orbit. So first of all, let's come back to the solar system for a second. Even though for the most part the planets seem to be in a relatively similar plane of orbit, there are some other objects like asteroids or things like centaurs or minor planets that do have relatively large inclination. Some of them are practically polar in their orbit. And there are at least 2 well-known examples, 2008 YB3 and 2004 YH32. Both of these objects have a relatively polar orbit, with one of them having approximately 80 degrees and the other one being in the opposite direction approximately 105 degrees. Which means that compared to the other objects in the solar system that have a relatively flat inclination, these 2 objects have a relatively high inclination. But at the same time, they also seem to have a relatively high eccentricity as well. And this does explain how they could acquire such an unusual orbit over time. This is actually related to one of the oldest videos on the channel in regards to this a slightly less known phenomenon known as the Kozai mechanism. Now that old video that should be popping up somewhere right there is actually pretty low quality, so my apologies for that, but you can also read about this mechanism in one of the articles from the Planetary Society. In a nutshell though, it refers to the idea of orbital interactions between 3 different bodies, and the body with very high eccentricity or very high inclination will actually end up exchanging them. So basically, high eccentricity becomes high inclination and eventually transforms back to high eccentricity but low inclination. It's a very unusual phenomenon, but I've simulated this using the Universe Sandbox back in the days, and today it's a pretty well-known phenomenon that explains a lot of high eccentricity or high inclination orbits such as various asteroids or minor planets. But this of course only explains smaller objects, so asteroids, minor planets, and possibly some really small planets. How do you explain a large planet, such as, for example, a mini Neptune, or an object that's basically as massive as everything else in the star system? And that's kind of the mystery of this unusual star system known as HD 3167. 3 confirmed exoplanets, but one of them is in practically polar orbit. And because all 3 planets also have relatively similar mass, it's extremely difficult to explain. At the moment, it's practically impossible to explain. But let's actually discuss first of all how this was discovered, because this is also important. So as I mentioned, this system was already known to us from some of the previous studies. It's about 150 light years away from us, and the 3 planets here have a relatively close orbit to the parent star. The farthest planet only takes about 30 days to complete a single orbit. And that planet right in the middle, with a mass of about 7 masses of planet Earth, has an orbit of about 8.5 days. That's the planet with that strange orbit. Now these planets were discovered using the transit method. Essentially, as the planet moves right in front of the star, it leaves a shadow behind that's visible using modern telescopes. But the thing is, the star also rotates, and as it rotates, it ends up producing what's known as the redshift and the blue shift effects. Or basically, the part that's moving away from us is going to appear slightly more red. The part that's moving toward us is going to appear slightly more blue. And so as the planet transits in front of the star, it's going to first end up blocking the part that's maybe redshifted, and then end up blocking the part that's blue shifted, which allows the scientists to work out several things about the planetary system and the way that the planet moves around the star. Specifically, it allows the scientists to work out the direction of orbit and also work out the overall inclination of the planet. And in the past few years, the scientists behind the study have actually perfected this technique, allowing them to discover a lot more properties about each of the planetary systems. But during their study, they've discovered that HD 3167c, that middle planet that I showed you previously, seems to have a highly misaligned polar orbit that you can kind of see right here. All of this discovered because as the planet passed in front of the star, it was only blocking the redshifted part of the star, which means that it never really passed anywhere here, which really makes this an extremely unique and practically impossible to explain right now star system. Okay, it's maybe possible to explain using some really far-fetched theories, but nothing that's sort of definitive. For example, one explanation here is that maybe there's a really massive planet somewhere on the outskirts pulling at just at one planet, for one reason or another. Or maybe this planet was just farther away or has extremely high eccentricity, and because of the Kozai mechanism, it sort of shifted its plane of orbit because of that massive planet on the outskirts. But that means that it has to have an extremely high eccentricity, something that would also be very difficult to explain. On the other hand, the only other star systems we know of that have these unusual mixed orbits, including polar orbits, are usually multiplanetary systems such as this one right here known as GW Orionis. This is still a newly forming star system, so the planets are not really there yet, but the way that its disk is forming right now suggests that its planets are probably going to be in somewhat misaligned inclinations, with some planets having really high inclination, but not really polar inclination, so once again difficult to explain. And also at the same time, these are multi-star systems, so it's a little bit easier to explain here because of the interaction between the stars. HD 3167, just like our Sun, is the only star in the system, so unless it lost its partner that used to exist here a long time ago, once again, super difficult to explain. Now there have been other star systems with unusual inclinations in their orbit, such as the Kepler 56 system that has a third planet slightly farther away, with an orbit of approximately 45 degrees, but once again, not as extreme and definitely not polar, so trying to explain this at the moment is not really possible. Since the original discovery of 3 different exoplanets in the 90s, the scientists have been able to discover nearly 13,000 different planets with quite a lot of features and quite a lot of properties not visible here in the solar system. Although most of these unusual planets so far have still not been confirmed, but they do probably exist. And when it comes to finding these planets, 2 methods have been used very successfully to discover the vast majority. The most successful method is known as the transit. That's essentially when we're looking at the star and trying to discover a tiny shadow passing in front of it. And over the years, some stars revealed quite a lot of different planets out there, allowing us to find several thousand different candidates, and that's of course the most successful method to date. Then we have another method that discovered approximately 1,000 different planets, known as the radial velocity. And that's essentially when the scientists look at the profile or the spectrum of the star they're looking at and discover that there's an unusual pattern where the star is redshifted and blue shifted with a very specific period. And that's because something is clearly orbiting around it. A lot of very massive planets have been discovered this way, and this method generally relies on just the observations of the color of the star, nothing else. Then we have the direct imaging method, where the scientists essentially cover the star and try to discover the planet by trying to see it directly. The James Webb Telescope was officially able to do so very recently, and you can find more about this in one of the videos in the description. But this of course relies on two assumptions. First, the planet has to be pretty far away from the star, and second, it also has to be warm enough to produce just the right frequency of light for us to see it, usually infrared frequencies, and that means that the planet has to be massive enough to have enough internal heat. This usually applies to Jupiter-like planets or something even more massive than Jupiter, not so much to smaller planets. Another interesting method that the scientists used before, and the one that was able to discover some of the most distant planets, is the gravitational microlensing. And that's where the star and the planet produce very tiny gravitational lensing effects, which are then visible as the planet and the star pass in front of a distant object. But unfortunately in this case, it's only really observable once, and this detection is not really going to be visible ever again for possibly up to 1 million years, meaning that this is a one-off detection. To date, a few hundred planets were discovered using this method. But then there is another method that's actually extremely difficult to reproduce, but produces some of the most accurate observations. The method known as astrometry, and that's when instead of looking for redshift or instead of looking for the planet, the scientists look at how the star moves around an empty spot in space and try to determine what's causing its wobble. In this case, by looking at the star, we actually can determine that the star is indeed moving because of the planet. And unlike the previous method using redshift and blueshift, this can often be extremely accurate because of various radio telescopes that can actually produce super accurate observations, such as the network known as VLBA, Very Long Baseline Array, a network of radio telescopes over 8,000 kilometers away from each other, creating a kind of a virtual planet-sized dish. And this is exactly what the scientists recently used to not just identify a planet in another star system, but to also create a first ever and also extremely accurate 3D map of the entire star system, along with the planet orbiting around one of the stars. In this case, looking at our neighbor, 20 light years away from us, a star known as EQ Pegasi. A star whose previous observations already established that it seems to be a binary system with two red dwarfs orbiting around one another. But the scientists wanted to find out more about the star system and wanted to actually see if they can create a perfect reproduction of how these stars orbit in 3 dimensions. And so they employed the Very Long Base Array telescopes to create an extremely accurate observations using astrometry. You can actually see how the star wobbled as they were observing it over time, with the bigger star here being about 44% the mass of our Sun, and the smaller star being roughly around 17%, with the average separation being about 30 astronomical units and a single orbit taking approximately 230 years. And one of the main reasons this system was chosen, apart from its distance to us, was because this actually represents one of the most common star systems out there. Nearly 75% of all of the stars in the galaxy are red dwarfs, and the vast majority of star systems is a binary, so this in a sense represents the most common type. But because the orbits here take so long, they actually had to rely on some of the older data going back in time as far back as 1941. But by using the modern data from the VLBA, they were then able to create extremely accurate map of the motion of the star in the night skies. And so using this astrometry method, to their surprise, they found a planet orbiting around one of the stars, because in that case, the star was actually wobbling a little bit too much compared to how it should be moving, with the planet determined to be a gas giant, very likely about twice as massive as Jupiter, but orbiting at a relatively high inclination of 150 degrees and also with an orbit of about 250 days, but more intriguingly and more unusually, orbiting in a retrograde orbit, in the opposite direction from the other star. And that by itself is already very difficult to explain. And if we were to imagine what the star system looks like, it might be something like this, with the planet being in this unusual location in the star system and the overall motion looking kind of like this. And so at the moment it would be relatively difficult to explain how the star system was created, but that's not really the point. The point is that, first, the scientists were able to even see this planet using this extremely accurate new method, and second of all, they were able to create this 3D map that extremely accurately represents what the star system looks like in reality, created using various models in order to see which of the models can actually fit the observations directly. But more importantly, it demonstrates that the astrometry has now achieved new heights. The improved sensitivity of various radio telescopes and the size of the network now allows the scientists to detect very small planets. As a matter of fact, it should technically be able to detect a lot of smaller rocky planets as well, similar to planet Earth. So in a sense, this was a kind of a test of technology or proof of concept, and it definitely worked. But that's just the first paper I wanted to discuss, because around the same time another paper came out discovering a completely new method that we can use to find even more planets out there. But the method that we can probably only use around relatively young stars. In this case, this is an object known as a T Tauri star. We've discussed these in previous videos, you can find it in the description, and it represents a kind of a baby star and still developing with an accretion disk around it, and also possesses a relatively large accretion disk around it. Although this one is much farther away, about 500 light years away from us, and it's mostly been imaged using radio telescopes such as ALMA. And because of the distances, and because this is basically a collection of dust orbiting around a young star, there's actually a limited way for us to generally find planets that are forming around these stars. One of the ways is to look for various gaps in the disk itself, such as the ones that you see right here, which can maybe suggest that there is a planet forming there as well. But in the last few years, the scientists determined that you can actually form these gaps in some other ways as well. So it doesn't always mean that there is a planet. But by looking close enough and by actually discovering something else here, it does become possible to discover where the planets really form. And so in this case, by zooming in and by looking closely, the scientists behind the recent paper discovered another unusual formation that's extremely difficult to explain unless it's a planet. They actually found very unusual arcs and very unusual clumps at very specific angles of 120 degrees, or technically 60 degrees and 60 degrees. And in general, when it comes to orbits, the 60-degree angle usually forms in a very specific situation when there are two massive bodies. We refer to these as Lagrange points. And so this right here, and also this right here, is 60 degrees, whereas this is 120. In order for something to form Lagrange points, you have to have some kind of a massive object orbiting a much more massive object such as a star. And so by finding these unusual clumps and unusual arcs at these very specific angles, the scientists now believe that right between them there has to be a planet that's maybe just a little bit more massive than Neptune, or possibly a little bit less massive than Saturn, located around a gap that's about 42 astronomical units away from the star itself, so around the same distance as Pluto is from the Sun. But in this case, the degree of separation is extremely important mathematically. Unless there is some kind of a massive object at this region, it's impossible to explain them otherwise. Having these very specific angles formed by chance is extremely unlikely. And so the scientists are pretty certain that this has to be a planet with a mass of a typical mid-sized gas giant. They don't really see it directly, but they see the effects that it's forming in the disk. And, if they are correct, they've just discovered yet another new method of detecting exoplanets out there. By detecting very specific clumps of matter, possibly asteroids or possibly just a lot of gas, at these very specific 60-degree angle of separation regions, it would definitely imply that there's a planet in between them. In this case, a planet that's probably around 3 million years old, and a planet that's going to have its own Trojans, just like Jupiter and other gas giants in the solar system, once it's done forming and once the star system disperses the disk around it. And honestly, in the last few years, all of these new ways of finding planets have actually really impressed me and have been super fun to follow. There's another video I released not so long ago with yet another method that finds more exoplanets, which also means that we're kind of entering a new golden age for finding even more exoplanets and for potentially finding new objects out there in our own galaxy. And in this case, it wasn't even using new telescopes or using some kind of a new analysis. The actual data was always there. It was just really applying some of the knowledge from the solar system and using the math of the orbits to discover something that was missed the first time. More about this in that paper in the description below. Hello wonderful person, this is Anton, and today we're going to be discussing a discovery of what seems to be a planet, but in a completely different galaxy, an extragalactic planet. And even though scientists have hinted on other extragalactic planets before, The discovery of this particular planet seems to be almost certain, and it actually was discovered using a very interesting technique. So let's talk a little bit more about this. But let's start with the idea of these extragalactic planets. Obviously, based on what we know about our own galaxy, we expect every other galaxy out there to possess a lot of different planets. But because of the distances involved and also because we can barely even tell a single star apart, it's almost impossible to find these planets using modern techniques. For example, you're probably aware that the majority of the planets in the Milky Way have been discovered using the transit method, by looking at the shadows of the planets passing in front of stars. But you have to remember that for these telescopes, like the TESS telescope or the Kepler telescope, when they're looking at these stars, all they're seeing is literally a single pixel. And the changes in brightness of this pixel, that's how they find these planets. If they were to use this technique by looking at another galaxy, in that similar pixel you'll actually have at least a few stars, possibly even an entire constellation. So trying to find an extragalactic planet using this, or any of the other modern techniques, such as the radial velocity technique, is currently practically impossible. Okay, so how exactly did the scientists discover 3 previous candidates? Well, in every single case, first of all, it was usually completely by accident. Second of all, they weren't even looking for planets, they were actually looking at quasars and were studying their emissions. And third of all, the actual technique was normally referred to as the gravitational lensing or microlensing. In this case, completely by accident, something very briefly passed in front of the quasar. And that something was very likely a small planet that then produced a microlensing effect. The effect that's been used to discover a lot of other planets, usually relatively close to the center of the galaxy. For example, the first such discovery was done back in 1996, and all of this was detected in the system you see right here. Now this is a galactic system, and if you really look closely at this image, you'll discover something a little bit unusual. It seems to have these 2 identical galaxies. Now, if you know anything about microlensing, you know that this is very likely the same galaxy, but it was just lensed by something in front of it. And that's exactly what happened here. The galaxy known as your Sirius galaxy, the one that you kind of see right here, is lensing this distant quasar, producing the gravitational lensing effect. And when the scientists were studying this back in 1996, there was actually a tiny dip of microlensing effect caused by a planet that was approximately 3 masses of planet Earth. And that was the first detection of a planet at a distance of about 4 billion light years away from us. Now the thing is, because this planet is not going to be passing in front of this location for probably a few 100 million years, or possibly ever, it's going to be impossible to replicate this and to actually confirm or deny this. And so naturally this is just a one-time detection, and the scientists think that they saw a planet. But at this point we don't know. Then we have this famous detection from 1999, a little bit closer to home, from the Andromeda galaxy. And once again this was detection of some sort of a planet, but this time by lensing a star. And the planet was probably about 6 masses of Jupiter, with the event known as this. Now you can read more about this in the link in the description below, but there is unfortunately not much we know. Once again, it's a one-in-a-lifetime event. It potentially contained an exoplanet, but chances are we'll never see this event again. And then the last detection using gravitational lensing was done back in 2018 from this beautiful quasar you see right here. This is known as Arrakis J1131-1231, and it's one of the most iconic images and one of the most iconic quasars that produces this beautiful Einstein's ring. But this time it seems that the scientists were able to discover a group of what's known as rogue planets. So these are obviously planets that don't usually have a star and travel completely by themselves. Normally they contain their own sort of miniature system. This was a pretty exciting discovery a few years ago, and even today nothing similar has ever been discovered just yet. But that's basically gravitational lensing in a nutshell. We usually find something once, but it's almost impossible to replicate this or to ever see this again. This time, however, the detection is very different, using a completely different technique, and in theory can be seen again and thus confirmed, although not anytime soon unfortunately. So here's what the scientists found. So first of all, this is once again coming from an iconic galaxy. In this case, a galaxy known as the Whirlpool Galaxy, or also known as M51. Now, even though we don't really see actual stars in this galaxy, we do see other really powerful objects. In this case, objects like black holes and neutron stars sometimes form what's known as the X-ray binary. That's essentially when a black hole or neutron star starts stealing mass from its partner and starts producing ridiculously powerful emissions. And so that's exactly what the scientists in this particular paper were initially studying. They were actually looking at the X-ray binary and were looking at this in the X-rays using the Chandra Observatory. If we were to look at the galaxy in the X-rays, this is roughly where this binary is located, which means that I guess it's somewhere in this region right here. And so here's the zoomed in image of what they were looking at, with the object itself, as you can see, producing several pixels, which is already a little bit more accurate than looking for a typical planet here in the Milky Way galaxy. So anyway, they were looking at these pixels, studying this particular binary, and during their analysis witnessed this, a dip. Now, normally these dips can happen for various reasons, mostly because these binaries are extremely unpredictable and they do produce a lot of various energy. So at least in theory, the emissions from the binary could have been changed by something entirely different. For example, it could have been some sort of a reshuffling of the magnetic field, which sort of temporarily stopped the emissions. But in this case, the emissions looked something like this. And that normally is a telltale sign that something just passed in front of the object, and usually that something has to be some sort of a planet. And that's pretty much what the scientists believe happened. They believe that a planet passed in front of this binary, temporarily causing it to dim just a little bit with just the same pattern that we've seen from a lot of different planetary detections here in the Milky Way. But instead of the optical light, this was in the X-rays. It just happened to produce the relatively similar observations. So in other words, this was a transit event, but it was an X-ray transit event. And assuming that this is indeed what happened here, this would be at a distance of about 28 million light years away from us, and the planet itself would be somewhat similar in size to planet Saturn. And on top of this planet seems to be orbiting the binary system. It's essentially orbiting the neutron star or a black hole, with the X-ray object itself being approximately 20 masses of the Sun. Now, because this particular event lasted for about 3 hours, this is sort of a telltale sign for a typical microlensing effect we've observed here from the Milky Way many times. So at the moment, there's almost no doubt that this is a planet, but it seems to be orbiting the system relatively far away from the center, at least 10 to possibly 20 astronomical units away from the center, which means that we might not actually see this object for at least 70, maybe 80, maybe even 100 years. Confirming this object would be somewhat difficult. Basically, by the time that this is confirmed, the current researchers are probably going to have grandkids. But this is of course just a preliminary investigation and just a preliminary discovery. There's still a chance that maybe this only has an orbit of just a few years, and we might see it again in the next decade. But obviously, a planet is just one of the explanations, even though currently it's the best explanation. This could also maybe be just some sort of a leftover from the early star system, some sort of a thick cloud. But at the moment the scientists don't believe so, and they still believe that this is a planet. Also, if this is a planet, it means that this planet survived the initial first supernova that created the X-ray binary, and there's probably going to be another supernova in the future from the larger star, which of course kind of implies that planets seem to be able to survive supernova and seem to still stick around the star system. But it's also important to understand that these particular detections are not very common either. They are actually kind of rare. As a matter of fact, the scientists in this paper weren't really specifically looking at the system for a long time. They were actually analyzing the data from the Chandra telescope that collected data from over 200 different X-ray binaries located in 3 different galaxies. The galaxy we just discussed, also the Pinwheel galaxy and the Sombrero galaxies. There were actually 119 similar systems in the Sombrero galaxy alone, but none of them exhibited similar patterns. Only in this particular X-ray binary showed us that there was a planet here, which suggests that, well, we probably are going to find more of them, assuming that we look at enough data. Many decades ago, early astronomers and a lot of science communicators used to think of Earth as just some average planet around an average star, in a somewhat average location around the galaxy, suggesting that many such planets should exist out there, and suggesting that many such planets should have habitable conditions, with many potentially hosting different types of extraterrestrial life, or even some kind of extraterrestrial intelligence. But in the last couple of decades, we kind of discovered almost the opposite. Not only is Earth seems to be extremely different from a lot of other exoplanets out there, so is our Sun, And so is the place where we are in the galaxy, meaning that this blue ball right here might actually be extremely rare compared to every other planet we've discovered to date. And with nearly 10,000 planets already identified and more or less confirmed by various missions, this actually makes it a pretty rare object. Nevertheless, there are some exciting planets that have been discovered so far that do have a slight chance to be maybe habitable and even potentially somewhat Earth-like or even hosting liquid water on the surface, with two that was just recently discovered being extremely interesting as well. Hello wonderful person, this is Anton, and so today we're going to be talking about this idea of potentially habitable exoplanets. We're going to discuss these two new discoveries and also talk about the planet known as Kepler 442b that you see right here, that for many years now the scientists always believed to be the most Earth-like planet we've found, but some of the recent studies actually argue with that. So let's discuss these concepts in more detail, and let's actually start with these new discoveries. And the first planet I wanted to take a look at was only found approximately a few days ago from when I'm making this video. Discovered by the TESS telescope and known as the planet TOI 1452b. TOI here stands for TESS Object of Interest. A planet that's very likely approximately 100 light years away from planet Earth, and was actually missed by some of the earlier surveys because this planet is located in a binary star system, and so some of the first observations did not actually recognize this to be a planet. And that's because normally in a binary system, as the two stars orbit around one another, they actually do produce quite a lot of dips, and these dips can kind of look like planets and can actually sometimes fool the scientists. And so in this case, the smaller dip around one of the stars was not seen right away. And in this case, these two stars also orbit around one another relatively closely, around 97 AU, which means that telling anything apart here is kind of difficult. But following a thorough analysis, one of the teams from Montreal was able to identify another dip around one of these stars. A dip that was caused by some kind of a planet that's about 1.6 times the size of planet Earth, orbiting around the star every 11 days. And normally this would be a problem, but in this case, because the star is a red dwarf, it actually places this particular planet right in the habitable zone of the star system, which of course means that it has a very high chance to potentially have liquid water on the surface. But once again, because this is a binary, it actually is possible to use some of the variations in the orbits to then also determine the mass of this planet, which is what the scientists were able to do. In the process, discovering that this planet is maybe about 4.8 times as massive as planet Earth, which intriguingly gives this particular planet very similar density to the density of planet Earth, around 5.6 grams per centimeter cube. Earth is about 5.5, which actually implies several things. First of all, this is a relatively dense object and is a terrestrial object, not some kind of a gas giant or some kind of a gas planet. But because of its relatively high mass, it also has a very high chance to potentially contain a lot of lighter materials as opposed to metals or different types of silicates. In other words, it implies that this particular object has a very high chance to be some kind of an ocean world. So kind of like one of the moons of Jupiter or Saturn, such as Ganymede right here that has a very large ocean underneath, with about 30% of everything here being water, except that in this case it's a much bigger object. It's a planet that's even bigger than Earth. And also, unlike Ganymede or unlike Europa or other moons, because of its location around the star system, the ocean here would be liquid, making this planet at the moment the best candidate for a potential ocean world ever discovered. We've actually talked about some of these objects in some of the previous videos. There should be one somewhere right there or in the description. But in a nutshell, this planet right now has the highest chance of having a really huge ocean on the surface. And 30% is way bigger than planet Earth. Here on Earth, the total mass of water is about 1% of the mass of the planet. And so potentially another interesting target for the James Webb telescope that can either confirm this or discover something else really intriguing in the process. Something we might learn about in the next year or so. So that's planet number 1. Then there's another planet that was recently found, I guess about a week ago, described in the paper that you can find in the description. This one is known as Ross 508. And once again, this is some kind of a super-Earth. Essentially a planet that's bigger and more massive than Earth by just a little bit, but not enough to be a gas giant. And so this planet, Ross 508b, is actually much closer, about 37 light years away from us. But what makes this planet interesting is the fact that it seems to have a very unusual orbit, where it essentially enters and then exits the habitable zone of the star because of its unusually elliptical orbit, making this a super intriguing target to study the potential habitability of these types of worlds. In this case, during its winter time, it might actually have liquid water on the surface, But then during the shorter summertime, the water might actually evaporate or at least disappear in some parts of the planet. And once again, because the orbit here only takes approximately 11 days, and this is once again a red dwarf, this is still a very intriguing target in order to learn more about potentially habitable worlds outside of the solar system. And just like the previously discussed planet, this one is about 4 times as massive as planet Earth, and is also slightly larger in size as well. Although what makes this discovery kind of exciting compared to the previous one is the fact that this is the first time ever the scientists found this by using infrared instruments on top of the Subaru telescope. In other words, this is the first planet ever discovered entirely by using infrared instruments, which once again means that James Webb here is going to be able to see this planet so much better because it's the biggest and strongest infrared telescope we currently have. And it also means that by using this technique, we can now identify even more similar planets, especially planets that are just too dim to be seen in optical light, but can still be detected using infrared, which is very often the case around red dwarfs. And the thing is, the vast majority of similar terrestrial planets so far have actually only been discovered around red dwarf stars. Mostly because these stars right here are basically like 90% of all of the stars in the galaxy. They're extremely common. G-type stars like our own sun are not as common at all. But several terrestrial planets have already been discovered around various red dwarfs, including the iconic TRAPPIST-1 system. There are like 7 of them around that one star. And so the question has always been, are these actually possible around those stars? And more importantly, if there's going to be liquid water, is it actually possible for some kind of extraterrestrial life to then begin the process of photosynthesis to start creating oxygen and to potentially evolve more complex life? Or basically, like this picture indicates, is it possible for Earth-like conditions to exist elsewhere, around some kind of a red dwarf or some kind of other type of a star? Well, first of all, in the last few years, there have been some really intriguing discoveries in regards to, well, essentially how photosynthesis works on the planet, and more importantly, how absolutely instrumental it has been to the evolution of the planet itself. Some of the videos about this are in the description below, but one of the more important discoveries is actually in regards to the mineral production on the planet. Over half of various minerals on Earth, the ones that are super important for life, or for chemical reactions involving life, have actually been created because of life itself. Specifically because of oxygenation and because of the oxygen produced by early bacteria. And because our planet had oxygen for nearly 3 billion years, and a lot of this oxygen was able to produce a lot of these new minerals, all of this is super important for the evolution of more complex life. And naturally, the most effective way we know of to produce oxygen is through photosynthesis. And even though several types of photosynthesis exist even on planet Earth, only the one involving chlorophyll seems to be the most efficient one. That's the one that really took off on our planet. And so can it actually also happen on these other planets, including the ones discussed earlier? And there's at least one study that did a very thorough analysis of this last year. The study that's also in the description below. Here the idea was really simple. They picked a planet known as the most Earth-like planet discovered to date, Kepler 442b. An exoplanet discovered back in 2015, and an exoplanet that's still believed to be most Earth-like object with the highest chance for potentially habitable conditions. Approximately 1.3 masses of planet Earth, and about 1.3 times larger than Earth. But more importantly, a planet orbiting a star known as a K-type star. A type of a star that's a little bit hotter than a typical red dwarf, but not as hot and not as massive as our own sun. These are actually slightly more common as well. And more importantly, these stars usually are able to live at least 3 to maybe even 5 times longer than a typical G-type star. Some of these stars can even survive for about 30 billion years. And that of course gives them a long time to potentially evolve so many things on the surface of those planets. Which is why this particular planet is so exciting for a lot of different scientists. And so here the scientists wanted to calculate the amount of photosynthetically active radiation, PAR as it's also known, that a planet received from its parent star. Because even if the star is really bright, but it's not able to produce just the right amount of light for photosynthesis to actually take place, the chance for any complex life here decreases dramatically. At least the types of life we find here on planet Earth, and based on what we know about planet Earth as well. While also trying to figure out if any living organisms here would be able to produce enough nutrients and oxygen in order to survive and maybe even thrive on this planet via normal photosynthesis. And what they discovered is that, well, it would be extremely difficult for anything around this star and on this planet to be as productive and as efficient in photosynthesis as on planet Earth. or essentially it would be a huge struggle for any life here to photosynthesize enough oxygen. It would still be possible, but it would not be possible to sustain a rich biosphere. And that's around a K-type star, that's also not as common as a red dwarf. Planets around red dwarfs, which have roughly around a third of the temperature of the Sun, could not possibly produce enough energy to even activate photosynthesis, suggesting that even if there's liquid water around these planets, the type of photosynthesis we expect around planet Earth would basically be impossible. Some other photosynthesis might be possible, but as far as we know it would not be nearly as efficient. On the other hand, the much hotter F-type stars or even B-type stars definitely produce enough light for photosynthesis to take place, but their lifespan is much shorter than G-type stars as well. And so the majority of more massive stars would have a lifespan of maximum 2 billion years, possibly not enough to produce enough complex life. Whereas the stars that are smaller than the Sun, K-type and M-type stars, just don't have enough light to have photosynthesis. Once again making the Sun-like G-type stars the only known star to us that seems to be able to host these conditions. And in this case, in the study, they actually studied 10 potentially habitable exoplanets known to us around different kinds of stars, and unfortunately failed to find a single match for Earth-like conditions or Earth-like atmosphere. Although since photosynthesis began so early on planet Earth, we kind of expect to find it at least possibly somewhere. And so some of the K-type stars, including this planet, Kepler 442b, still have a chance to have maybe some photosynthesis on the surface, but not a complex biosphere like planet Earth. It might be possible for some of the life here to create photosynthesis using longer wavelengths, around 800 nanometers or infrared light, but at the moment we don't really know of any such organisms on planet Earth. Any photosynthesis around Kepler 442b would have to rely on only red light. But it doesn't change the fact that they could still have liquid water. It's just the water here would be most likely devoid of life or only have extremely simple life, able to just produce a little bit of oxygen or a few chemicals here and there. Or potentially bacteria using some kind of a chemical reaction to produce all of the energy, similar to, for example, archaea here on planet Earth. Nevertheless, when it comes to Kepler 442b, at the moment, even though this is the most Earth-like planet discovered, the chance for complex life here, or possibly even any life, is extremely low. Some bacterial life might survive, very primitive life, but nothing too advanced, and definitely not something using photosynthesis similar to planet Earth. So chances are we're not going to be finding a lot of oxygen around this planet. And this, by the way, is going to be super exciting to find out in the future studies using James Webb Telescope, because this is definitely going to be one of its targets. In the last few years, we've discovered quite a lot of different exoplanets, with some of them extremely close to their parent stars. So close, as a matter of fact, that the scientists suspect some of these planets are stretched into unusual shapes, in some sense resembling an egg or a rugby ball. And although for the most part this was just a theory up until this point, in this particular paper the scientists have finally confirmed that the most likely candidate for this unusual shape, the planet known as WASP 103b, indeed seems to be egg-shaped, and they've been able to officially confirm it using one of the ESA's telescopes known as Cheops. Hello wonderful person, this is Anton, and today we're going to discuss this paper that, as always, you can find in the description below, that officially confirms that some planets, the ones that are really close to their parent stars, are dramatically influenced by the tidal forces to the point where they do indeed transform their shape. But more importantly, some unusual discoveries come from the star system, with some unusual mysteries that the scientists currently cannot explain. But let's start with the basics. So, we all know about tides. So basically, because of the gravity, or the objects pulling on each other, there's usually some sort of a deformation that sometimes is more visible than other times. For example, on planet Earth, most of our tides are usually caused by the moon, with certain other tides caused by the sun as well. But the tides on Earth are nothing in comparison to some of the other objects in some other star systems that are usually much closer to their parent stars. So there is at least one such system that the scientists have actually been really curious about. It's a system known as WASP 103. And the star here is extremely similar to our own sun. It's actually maybe a little bit hotter, it's an F-type star, and it's also a little bit younger. With the host star also obviously having a planet around it, relatively close to it, with a single orbit here taking roughly around one single day. With the planet itself, that you can kind of see right there, most likely being very similar to Jupiter, but a little bit larger and also a little bit more massive. And one of the main reasons the scientists have always been sort of wondering about this planet is its unusual structure, or actually its unusual size in comparison to some of the other similar objects. And so first of all, this is approximately 1.5 times the mass of Jupiter, but surprisingly it's double the size of Jupiter. And at the moment this actually is very difficult to explain. For some reason this planet seems to be a little bit larger than it should be, or basically it's sort of inflated. Now this was originally assumed to be due to the proximity of the star, but at this point nobody actually knows why this is so. Normally you would expect these objects to be much closer in size to Jupiter, and here's what Earth looks like for comparison as well. And because of the proximity of this planet to its parent star, this particular exoplanet always had the highest chance of having the deformation signature, or basically being not spherical. And that's because it's actually really large, and because the star itself is also really close to it. As a matter of fact, the planet is only about 10% the size of the star itself. And as you can see from this image made by the European Space Agency, and also as you can see from this simulation, the planet definitely seems to be extremely close to its parent star. And theoretically, the proximity here would suggest that the planet experiences tremendously powerful tidal effects, so powerful that the planet would be stretched into an egg shape, possibly even more egg shape than simulated here. But because this planet is also very far away from us, over 1200 light years away, it's been kind of difficult for a lot of previous telescopes like Hubble telescope to actually identify these patterns in order to establish its true shape. So up until this point, all of this was extremely theoretical and not physically proven just yet. But the scientists behind this paper managed to collect enough data from several telescopes to finally prove all of this. And specifically, they've used several transits from Hubble telescope and Spitzer telescope, but more importantly, from one of the cheaper telescopes that's currently operational and that's currently orbiting planet Earth, the telescope you see right here known as Cheops, characterizing the exoplanet's satellite. And this is actually a really interesting project. First of all, it was relatively cheap when it comes to space telescopes. The total cost here was approximately 50 million euros. This telescope was only launched a couple of years ago and only started operating in 2020, but has already made some major discoveries, including discovering several planets in the system known as TOI 178. And since this is a relatively small telescope, it's roughly around 1.5 meters in every direction, with the mirror itself only being approximately 30 centimeters, a lot of the discoveries it's been making so far are somewhat impressive. But more importantly, what exactly is this telescope for? Well, its main purpose is to actually try to determine sizes of various planets that have already been discovered using other methods. And specifically here we're talking about planets like the ones discovered using the radial velocity method, where we only know their mass. By only knowing their mass, we are unfortunately unable to determine anything else about these planets, specifically their composition, their density and so on, and normally we only assume that these are gas planets. But by using this particular telescope, the scientists can now also try to measure a very precise size of the planet, and by knowing the size and the mass of the planet, they can then start to make assumptions about its density, its composition, and possibly a lot of other properties, including what it could be made out of. That's normally determined by looking at the actual light passing through the planet's atmosphere and then by seeing what sort of elements are visible there. And this particular telescope is surprisingly accurate and surprisingly precise in its measurements, able to see some planets that a lot of other telescopes usually don't even notice. And so in order to prove that some planets are indeed tidally disrupted and have unusual shapes, the scientists in this paper decided to focus on that one planet that everyone always assumed to be egg-shaped. And by combining 12 different observations from Cheops along with the models they created in order to see what a lot of these passages would look like if this planet was slightly deformed, they've officially confirmed that this planet is indeed extremely stretched, and for the most part also seems to be very flexible. In other words, it's not rigid like a typical rocky planet. And this is of course something we would expect from a typical gas giant like Jupiter or Saturn. In this case, it's assumed that there is probably some sort of an atmosphere, some sort of a fluid layer on the inside, and most likely some sort of a solid core as well. As a matter of fact, in this paper, the scientists have even gone as far as calculating what's known as the love number, the number that's usually used in astronomy to determine the rigidity of a typical object. And the higher the number, the more flexible or not rigid the object is. And in this case, the Love number of this planet seems to be extremely close to the Love number of planet Jupiter, naturally confirming that this is some sort of a egg-shaped gas giant. But these observations have also presented a new mystery. So normally, when it comes to these planets orbiting very close to their parent stars, and when it comes to tidal interactions between these objects, in the past, pretty much all of these so-called hot Jupiters would slowly approach the parent star, with the actual approach being even visible in some of the initial calculations. In other words, over time, a lot of these planets come closer and closer to the parent star and would most likely eventually fall apart, forming some sort of a ring around the star, which slowly makes its way and falls into the star itself. Now, that particular part has never been observed before, but that's kind of assumed theoretically. But the mystery with this planet is that, first of all, it's already basically at its limit right before it falls apart completely. So basically it's at the limit of its tidal disruption. But when observing the orbital parameters and changes of this planet, the scientists determined that not only is it not moving closer to the star, for some reason it's slowly moving away from the star. Now, it hasn't been confirmed just yet, but these initial observations suggest that something else is happening in the star system, with one potential explanation possibly being another star somewhere in the vicinity. A star that you see sort of present possibly right here. And if there is a partner star, it could maybe pull on the planet and slowly cause it to move farther and farther away from the parent star. But then there are other questions. First of all, how exactly did this planet end up here originally, and why didn't it fall apart yet? Second of all, if this other star was pulling on this planet for a relatively long time, it's sort of assumed that the planet probably came from much closer to the parent star. But it's already almost at the limit before it falls apart. So in that sense, it actually wouldn't make sense that this planet would exist at all. In other words, there are currently a lot of questions in regards to the origins of this planet and, of course, its migration in this particular star system. And that's because the way it looks right now, well, if this planet was indeed formed in this star system and was slowly moving farther and farther away from the parent star, it means that at some point it wasn't a planet. It might have been some sort of a ring formation or something entirely different. But that's obviously not how we believe planets are formed, and so a new mystery for the scientists to figure out in some of the future papers. For now, it's actually a pretty cool confirmation of a known theory, and definitely a really cool analysis using one of the most interesting telescopes, whose main purpose is to identify more properties of various planets already discovered by other telescopes. So in that sense, great job, Cheops. But for now, I guess that's all I wanted to mention. Hello wonderful person, this is Anton, and today we're going to be discussing a confirmation of a very intriguing exoplanet, or I guess technically an exoplanet in the making. The exoplanet that proves an idea behind planetary creation. Certain planets can be actually made in a very different way from most of the planets out there. With this particular exoplanet, baby exoplanet, located about 530 light years away from us, potentially helping us confirm a known theory known as disk instability formation, a theory that suggests that certain planets can form directly from the protoplanetary disk when the disk sort of starts to clump into larger chunks and when all of this gas then starts to coalesce into a large enough object. A theory that has never really been officially proven and no example has ever been found until now. And so let's discuss this idea in more detail and what this means for, I guess, the future of astronomy as well. But let's start with the star system. So where exactly is it and what is it? This star is known as AB Auriga, located in the constellation of Auriga that you see right here. And it's a star that's somewhere inside the very well known Taurus molecular cloud, where essentially a lot of baby stars are being born right now. With the star itself very likely eventually becoming what's known as an A-type main sequence star, approximately 2.4 masses of the Sun in mass, with an average temperature of anywhere from 9,000 to 10,000 Kelvin. But that's of course in the future when it officially forms into a main sequence star. At the moment it's still not. It's actually what's known as a Herbig AE star. A baby star that's still surrounded by a huge amount of gas, usually even hiding from everything by this gas, and a relatively brand new protoplanetary disk. And so most of the observations of this particular star system were actually done not in the optical light, but in other light, for example, radio light. In this particular case, what you're looking at is an image created by ALMA using the microwave frequencies. with the disk formed around the star being relatively large, approximately 120 astronomical units, suggesting that it has quite a lot of mass on the inside. But it's also been discovered that it seems to possess a kind of a gap on the inside, which might have been caused by some sort of a collision early on, with the unusual spiral arms you see right there very likely containing a lot of carbon monoxide, basically a lot of organic compounds which very likely are going to form much more complex molecules later on. It's also been discovered that this particular system, like a lot of other baby systems, seems to contain what's known as a stellar jet, which is not really uncommon for early star systems, and in this case it's causing the star to lose just a little bit of mass, with the velocity of the jet being approximately 300 km per second. But it's really the observations over a period of approximately a decade that allowed the scientists to discover very dramatic changes in the protoplanetary disk itself. In this case, the observations from 2007 that you see right here, compared to observations relatively recently in 2021, revealed the formation of an unusual clump-like object approximately 93 astronomical units away from the center of the star, roughly around 3 times the distance of Neptune to the Sun, with further observations later confirming that it seems to be some kind of a protoplanet, in this case a really massive protoplanet, most likely about 9 times the mass of Jupiter, but orbiting really far away from the parent star. And to the astronomers, this was an extremely exciting discovery. There's a really simple reason for it. Today, it's believed that most planets, or I guess technically all planets, form as a result of what's known as the core accretion model. Essentially, little objects become bigger objects through collision, with larger and larger pebbles becoming planetesimals, and those planetesimals, as they collide, becoming protoplanets, eventually turning into planets. With, for example, objects like Arrakis that was visited by the New Horizons probe, presenting a perfect example of a planetesimal that never really turned into a planet. And larger and more massive objects located in the asteroid belt, such as for example Ceres or Vesta, representing a typical protoplanet. In other words, there were always plenty of examples proving the so-called core accretion model, which always suggested that this is how very likely all of the planets out there form. But there have always been other models, and one of the bigger models that suggested how certain planets can form is the idea referred to as disk instability model. The model that for the most part has always been proposed using various computer simulations and suggested that certain very massive planets, even planets like Jupiter, could technically form when there is some kind of an instability in the protoplanetary disk, with the instability causing a sudden collapse and a sudden clumping of all of the matter, which then suddenly forms a planet that's massive enough to be a potential brown dwarf or even a planet like Jupiter, with the major difference between core accretion and disk instability being the timeline itself. In this case, all of this would happen extremely quickly. Within just a few thousand years, the planet would be almost completely finished. Whereas for a core collapse model, this would be a much slower process and would even take up to 1 million or even 2 million years. But except for computer simulations, this unfortunately has never really been seen anywhere. It's never really been officially proven. And that's of course, I guess, until now. Until the recent observations from A.B. Auriga that lasted for over a decade. In this case, only discovered because of the Hubble's resolution and because of the longevity of the mission. Because the Hubble telescope has been operational for several decades and has been looking at various objects repeatedly for many years, it allowed the scientists to see actual changes in various baby planets out there and to then analyze these changes, determining what's happening in those systems. And so the most recent image captured by the Hubble telescope back in 2021 discovered that this particular object definitely moved counterclockwise in this particular star system. And it also seems to have collapsed into something a little bit more dense. And although at this point it's not necessarily a definitive proof of the so-called disk instability model, it's definitely the best example we have so far that a typical instability from, for example, a star passage or some other unusual gravitational event that causes the disk to become somewhat irregular can then result in a sudden collapse of a lot of matter, which can then form some kind of an object, potentially another star or potentially an actual planet. Something that has definitively been created in a lot of different computer simulations. Suggesting, of course, that there's very likely not just one or even two ways of creating planets, there potentially are many different ways for various star systems to form various planets. We just haven't really explored or understood the actual processes simply because we've only been doing this for a few decades. We're going to discover more of these unusual formation systems once better telescopes such as James Webb Telescope become operational and fully functional. And in this case, it seems to have happened because of some kind of a very violent event, something that's also visible in the shape of the disk and the unusual spiral arms created here. Whatever happened in this unusual star system a few thousand years ago most likely disturbed the outer section of the disk and forced various parts of the disk to collapse into larger chunks. And because there is no other explanation for how such a large, dense object could form so far away from the star, at the moment the disk instability and some kind of a violent event that caused this is the most likely explanation. Because through the core accretion process that we believe forms a lot of other planets, it would take millions of years to create something like this, and this particular star system is less than 2 million years old, so in theory it would be impossible. But in this case, that's pretty much the only thing we know about this object right now. Only the future telescopes might be able to explore some other details, including the potential composition of this planet, but it would require a lot of other additional observations using other frequencies. In this case, James Webb Telescope is definitely going to be super helpful, but for now that's unfortunately all we know. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries in regards to this somewhat unusual exoplanet you see right here, known as WASP-121b, a planet that was already quite extreme when it was originally discovered, but has now been confirmed to be even more extreme, possessing one of the strangest water cycles we've ever seen anywhere. But more importantly, in this video, we'll be talking a little bit more about these very unusual hot Jupiters, many of which have been discovered in the last few years, and the most thorough analysis of the atmosphere of such planet, with the recent study doing a very good job at allowing us to see what happens in the atmosphere of this planet, both on the dark side and of course on the side facing the star. But to start, so where exactly is this planet and what sort of a planet is this? WASP-121b is essentially a typical gas giant, as you can see from this NASA simulation you can find in the description below. And it's located about 880 light years away from planet Earth, orbiting what's known as an F-type star, a star that's slightly larger and more massive than our own Sun. But even though generally in terms of mass and in terms of size, this planet is somewhat similar to Jupiter, due to its proximity to the star, it actually possesses a lot of properties we cannot even imagine. And so for many decades now, the scientists were trying to figure out exactly what happens around these planets, how exactly these planets form, and more importantly, whether such a planet existed in the solar system sometimes in the past. Mostly because these seem to be extremely common across various star systems, but they don't seem to exist anywhere near us. But because of their size and their mass, they are generally relatively easy to find. As a matter of fact, one of the first exoplanets to have ever been confirmed was this exoplanet right here, known as 51 Pegasi b, also known as Bellerophon. So because of how common these particular planets are, it's always been super interesting for the scientists to figure out what happens in their atmosphere, and more importantly, what happens in the atmosphere of tidally locked planets. Planets with one side always locked toward the star, and the other side always away from the star. And because these are such common objects and have been discovered in pretty much most of the red dwarf systems as well, with various planets being tidally locked for one reason or another, it's actually really important for the scientists to try to figure out what happens to the atmosphere in these very common planetary systems. Moreover, because so many different hot Jupiters have been discovered and so many have been already confirmed by various investigations, and also seem to interact in a very unusual way with the parent star itself, a lot of these investigations have been extremely important in order to understand how various star systems evolve. For example, we know that several different systems have already been discovered where the hot Jupiter orbiting the star, usually with an orbit of less than approximately 30 hours, often interacts with the star in different ways. Specifically, it actually even causes various flares on the star's surface because of the magnetic interactions. We also know that generally these hot Jupiters will unlikely to have any moons or possibly even planets near them, mostly because they're too close to the star to maintain permanent moons, and their gravitational interaction with nearby planets will also cause some of those planets to either be absorbed by the star or by this particular planet. Not to mention that some of these hot Jupiters have been discovered to be extremely odd. For example, WASP-12b is known to be one of the darkest, if not the darkest, planets to have ever been found. Some of these planets also turn into what's known as poofy planets. They expand to tremendous radii. And some of them even develop a sort of a connection to the star, where the star starts to slowly absorb the planet. And so being able to have a very detailed analysis of at least one of these hot Jupiters is actually really important, just to see how things work somewhere out there. So what exactly did the scientists discover in this particular case? So first of all, this is at a distance of just over 800 light years away from us, and a single orbit is roughly around 30 hours. And one of the first discoveries coming from this planet is in regards to the brightness of the day side versus night side. It seems that the night side is about 10 times fainter than the day side. And this is actually really interesting because you'd expect the night side to be much darker, but it's not, very likely because of the super high temperatures around this planet, and because even the dark side sort of glows because of the temperatures involved. And the temperature difference is quite extreme. On the day side, the maximum temperature is around 3000 Kelvin. At this temperature, there are very few elements, actually like 3 or 4 elements, that do not melt. Everything else would melt or even evaporate. But the dark side is a little bit cooler. It's approximately 1500 Kelvin, which means that a lot of things that melt on the day side will then most likely condense on the dark side. And some of the previous studies have already discovered the presence of water around this planet. And this paper established that there's definitely a water cycle, but not the same water cycle as the one on Earth. Here the water molecule completely falls apart on the day side, just to then recombine on the dark side when it gets a little bit cooler. In other words, the day side only possesses hydrogen and oxygen and a lot of other materials, but then as the atmosphere moves around to the dark side, it sort of changes back into water gas. You can actually see how all of this changes depending on the position of the planet around the star by looking at one of these simulations in the description below. And obviously right now nobody has any idea what this type of a water cycle would do to such a planet. It's very likely that because the gas is present on the dark side, it might actually do something to the atmosphere and potentially even have certain effects on the planet that are not really understood just yet. With the water cycle itself being sustained by extremely fast-moving winds that were detected in the study. Here, the winds whip around the planet at 5 kilometers per second. But naturally, water is not the only thing on this planet. As a matter of fact, it seems to possess a lot of stuff. And most of the stuff does the same thing. It goes through various cycles between being a gas to potentially being a liquid. For example, the scientists have discovered that there's quite a lot of corundum, the stuff that we usually find in different sapphires and different rubies, and several other elements including magnesium, iron, vanadium, and what's known as perovskite, all of which create different types of exotic rain in the atmosphere of this very unusual planet. So this planet doesn't just have iron rain, it seems to have sapphire rain, ruby rain, and possibly a lot of other rains we can't even imagine just yet. In the process, also discovering that, unlike other planets in, for example, the solar system, the temperature changes on this planet are also kind of unusual. For example, on the day side, the temperature actually increases with altitude. Deeper in the planet, the temperature is about 2500 Kelvin. On the outskirts of the planet, it's about 3500 Kelvin, a 1000-degree temperature difference, whereas on the dark side, it's the opposite. The temperature decreases from 1800 Kelvin deeper in to about 1500 Kelvin on the outskirts. And this unusual thermal inversion, as the scientists refer to it, is at the moment somewhat difficult to explain, but also very likely creates a lot of properties for this planet and a lot of similar planets that we cannot really understand just yet. With the hottest point of the planet being in the east on the day side, mostly because of the extreme winds on the surface that transfer all of this heat into the eastern direction. And as all of this gas travels across the day side, it gets heated up by the star and increases in temperature until that eastern point, with the entire atmosphere of the planet recirculating every 20 hours. But now the next step for the scientists is to try to use some of the time on the James Webb Space Telescope to try to see if they can also find some of the carbon present in the atmosphere as well. Because by discovering carbon, and specifically carbon monoxide that could be present here, the scientists can finally figure out how these planets form and where exactly they actually come from. And figuring out their origin and why they don't exist in the solar system has always been sort of the biggest mystery in regards to hot Jupiters. Hello wonderful person, this is Anton, and today we're going to be exploring something from a very famous science fiction book / movie, something that I've been meaning to make for a very long time. We're going to be exploring Arrakis from the famous novel by Frank Herbert, Dune. But more specifically, I'm going to be focusing on this relatively recent article that, as always, you can find in the description below, that answered a simple question. Could the main planet from Dune, the planet known as Arrakis, actually exist in real life and potentially be the way it's presented in the movie and, of course, in the novel? And this is a type of a topic I used to cover on the channel quite a lot. For example, there's an entire series of different older videos where I tried to recreate various planets from Star Wars and try to see if they could actually exist in real life as well. And I also did the same with a few other science fiction and fantasy novels, including, of course, the famous Game of Thrones. But in this video, I really wanted to finally focus on Dune, mostly because I just finished watching the movie and it was pretty good, not as good as maybe the original 1984 version, but still pretty good. And more importantly, because of this recent analysis / article that basically did a lot of legwork in trying to scientifically determine if such a planet could actually exist. Now, in case you've never watched Dune or in case you've never read the book, well, the premise is really interesting. It's probably one of the most engaging science fiction novels in existence. It involves a lot of different topics, including a really important environmental theme, and it's even been referred to as the first planetary ecology novel on a grand scale. But it's also a novel that involves a lot of intrigue, a lot of betrayal, and essentially this unusual planet located approximately 300 light years away from planet Earth that seems to possess these unusual worms that produce unusual psychedelic element. The element or the spice referred to as melange, with the iconic phrase explaining what this is. The spice extends life, the spice extends consciousness, the spice is vital to space travel. Or in other words, it's a drug that seems to transform humans into something entirely different and is the only way humans are able to travel across vast distances in space. So it was actually a really cool concept. And the planet known as Arrakis, the desert world with practically no water on the surface, is the only place where you can actually find this spice. But anyway, if you haven't watched the movie yet, or if you've never read the novel, I don't want to spoil the rest because it is pretty fun. And so could such a world really exist somewhere out there around a certain type of a star? First of all, I actually wanted to start with something that's not mentioned in the article, the star itself. And it's one of the brightest and one of the most well-known stars in the night skies. It's a star you see right there. It's known as Canopus, also known as Alpha Carina. Now the thing is, if we jump to the star, you'll probably quickly realize that it's basically blindingly bright. It's extremely bright. It's also really large. It's about 8 times the mass of the Sun. Let me actually lower the luminosity a little bit. And it's what's known as an A-type star. But it's also only about 25 million years old. The first improbability from the novel is the fact that this planet seems to have some sort of complex life on it. 25 million years is unfortunately not really enough for life to evolve even on a planet like Arrakis. And so this is something that was not actually considered by Frank Herbert back in the days. But planets here are definitely possible, and some of the planets here are going to be extremely hot and be exposed to quite a lot of different types of ultraviolet radiation. Now in the novel, this is the 3rd planet away from the star, so kind of like Earth. But in our simulation in Space Engine, this planet is a little bit too toasty to survive on. The average temperature here is roughly around 2000 degrees Celsius. But naturally, some of the farther planets could potentially have the necessary conditions to have just the right temperature. Unfortunately, no planets have been discovered around Canopus to date, but they're probably there, they're just maybe not as easily visible. So in other words, the existence of Arrakis is kind of possible. But how realistic is everything else in the novel? And so the scientists behind this article are actually experts in climate simulations. And to try to simulate all of this, they kept the same fundamental physical laws that create climate and weather here on planet Earth. In other words, they use the models and the simulations that are normally applied to study climate and different types of changes in climate here on planet Earth. For example, by using the link in the description below, you can find this website right here, where the scientists have already simulated various types of changes in climate as our planet evolved in the last 500 million years. So for example, right around here, you can sort of see how the planet looked like in terms of different climatic conditions during the Jurassic era. And so by going through different era, you can see how the climate changed as the continents moved around and as a lot of bodies of water changed in size and shape. Then they also have a really interesting and a quite realistic simulation of what might happen to our planet if essentially we don't stop releasing CO2 and if the climate change does not become any better. In this case, they show us what happens to the world if we agree to reduce the emissions of CO2 and a lot of other greenhouse gases, and what happens to the climate on the planet if we sort of ignore all of this and pretend like it doesn't exist. This particular simulation is very convincing. And all of this was done by running these simulations for up to about 3 weeks by running it on a supercomputer. And this time the scientists decided to go in a slightly different direction. They wanted to see what would actually Arrakis look like. And so by using all of the parameters from the novel and also from some of the other sources like for example on Wikipedia, they built the model of the planet using its topography, using a very specific orbit mentioned in the novels, and also creating a specific type of an atmosphere as well. In this case, it's somewhat similar to planet Earth in terms of the content of CO2, although the actual CO2 levels here are basically what we used to have in 1950s, so here we're talking about 350 ppm. Unfortunately today the levels are a little bit higher. But on top of this, they also added a lot more ozone to the planet itself. And so even though on planet Earth ozone only represents a tiny fraction of the entire atmosphere, on Arrakis it's 0.5%. And because ozone is a very strong greenhouse gas, this in some sense could explain why Arrakis is so hot and is basically a desert world. Also, one of the potential explanations for how so much ozone was created here is really because of the star itself. The A-type stars in this case produce way more UV radiation, and when the UV radiation in the upper atmosphere interacts with oxygen, it ends up producing ozone. So if there's more UV radiation, and I guess if there's more oxygen, you're going to get a lot more ozone. At least that's my take on this. It's not really explained in the article. And so once all of the parameters were plugged in, and once the supercomputer finished its calculations, they produced this. And turns out that it seems to be an actual planet that could potentially exist, with parts of this planet being potentially habitable, but there were some parts that weren't really adding up. In other words, some parts were basically fantasy or science fiction. And so let's briefly discuss some of this. So first of all, this simulation allows you to look at pretty much every region of the planet and discover what some of the regions here might look like, while also providing you with the average temperature in certain parts of the planet. Something that you can also see right here, this was provided by the authors. And interestingly enough, in the warmest month right here in the tropics, the temperature is roughly around 45 degrees Celsius, or about 113 Fahrenheit, whereas the coldest months reach the temperatures of about 15 Celsius or about 60 Fahrenheit. And so here the tropics seem to be quite habitable. And here we're obviously talking about the region relatively close to the equator. You can kind of see in the simulation how the temperature changes. But on the other hand, some of the most extreme conditions in terms of temperature seem to actually occur in the mid-latitudes and the polar regions, with winters being as cold as minus 40 degrees Celsius or minus 40 Fahrenheit, and sometimes even colder, minus 75 Celsius, so kind of similar to what we have in the Antarctica. On the other hand, the summers are extremely hot, up to about 70 degrees Celsius. That's close to about 160 Fahrenheit. So essentially, the summers here would be impossible to survive for any inhabitants on this particular planet. And remember, in the novel, we're talking about regular humans that didn't really evolve much. Yeah, they have these really cool suits that protect them to some extent, but 70 degrees Celsius is still really hot. But in the book, we know that the two major cities are located in the polar regions, where the author assumed it would be a little bit cooler, a little bit easier to survive. Turns out the simulations show us the opposite. It looks like it would be much easier to survive on the equator, not really in the polar regions. And that's actually a little bit surprising, it's a little bit counterintuitive. And I guess the next question is, why is this happening? Because that's also kind of opposite of what we find on planet Earth. Well, the answer becomes a little bit more apparent if we start investigating what happens to moisture on Arrakis. There's not a lot of moisture, but there's some. On Arrakis, as you can see from these clouds right here, there is just significantly more moisture in the polar regions compared to the equator. And there are also a lot more clouds here as well, and all of this water vapor acts as a very potent greenhouse gas, warming up certain regions more than other regions. And even though the book says there's no rain on Arrakis and water is extremely difficult to find, this particular model suggests otherwise. It still produced just a little bit of rain and just a few clouds here and there. Although in this particular case, there would be only certain regions where rain would occur, for example in the mountains. At the same time, the book suggests that there were actually polar caps on this planet as well, especially in the polar regions, or basically that there was permanent ice. But this model definitely suggests that these polar caps could not possibly exist. Even though it gets cold in the North Pole right here, it does also get extremely hot in the summer. So the polar caps would just not survive for the whole year, and it would be impossible to produce large caps because the temperature here shifts pretty much every single year. Okay, well, despite these small differences, the planet is still habitable, especially in the equatorial regions. And these tropics would be able to provide just the right conditions for a lot of different life to survive here. Although by traveling a little bit to the north or a little bit to the south, in certain locations in the lowlands here, the future humans might actually find themselves in very inhospitable conditions, and the farther they go, the more extreme it becomes. On top of this, interestingly, on this planet, outside of tropics, outside of the equatorial region, the winters become really extreme, but in the tropics, the winters are more or less mild and the actual conditions are more or less pleasant. But the two cities mentioned in the novel, known as the Arrakis and Carthage, would most likely be extremely difficult to survive in. Here, this would be very cold in the winter and extremely hot in the summer. The authors actually compare it to some of the cities in Siberia, for example, where the conditions are just too extreme. Obviously, it's possible to survive, but they would not really be major cities like the ones we see in the novel and in the movies. But naturally, you also have to remember that this novel is pretty old. It was originally written back in 1965, and this is before we had these really advanced models or these advanced simulations, or before scientists even knew how to model climate changes. And so for a novel that's several decades old, this is actually pretty good. And so to answer that first question of whether Arrakis could be habitable and if humans could survive here, the answer does seem to be yes, and a planet like Arrakis could definitely exist. Hello wonderful person, this is Anton, and today we're going to be talking about what seems to be the first ever observation and confirmation that there are definitely star systems out there where there are actual planetary sized collisions happening at this time. With the recent study that as always you can find in the description below, detecting, observing and calculating what seems to be the collision between relatively large planetesimals a few hundred kilometers across. In this case, all of this happening over a period of several years. All of this reported in this paper right here, around a star known as HD 166191, a star that's roughly around 10 million years old, located around 330 light years away from planet Earth. And in this case, the observation and the analysis are extremely interesting, especially in helping us understand how various star systems very likely evolve, and more importantly, how planets like Earth have formed in the past. But I guess let's talk a little bit more about the details and what exactly the scientists were able to detect and how they were able to do it. So first of all, here we're not talking about asteroids or actual planets. We're talking about what we usually refer to as planetesimals. The large pieces of material that clump together forming various rocky bodies, and that then, by colliding with one another, produced objects like planet Earth. Now this one is probably the most well known in the solar system. This is the object we sometimes refer to as the Arrakis, the object visited by the New Horizons probe a few years ago. With this representing the material that existed in the solar system for a very long time, but in this case never really materializing into any particular planet. And that's of course because as a lot of these objects collided with various other objects in the early solar system, some of them ended up producing larger planets, other ones ended up producing smaller asteroids, which were basically leftovers. And yet other ones, like Arrakis, ended up getting kicked out to the outskirts of the solar system where they still are today. At least that's the general explanation we have today based on a lot of the observations we've done of a lot of different star systems out there. Some examples right here. These two systems are only a few million years old and they seem to possess quite a lot of material representing what we would normally call a planetesimal, an object large enough to then start forming larger planets. But even though we can generally see various protoplanetary disks and various early stars out there, and we can generally see some of the dust and even the material present in those particular star systems, being able to prove that various planets grow through the collision of these objects has always been kind of one of the goals of modern astronomy. In other words, trying to prove that this is a planetesimal that could have become a planet is of course one of the reasons so many observations are done across the entire galaxy. And so several studies in the last few years, especially studies conducted in the infrared light, the ones usually producing pictures like this one showing us the protoplanetary disks, have been actively looking for signs of various catastrophic collisions between various planetesimals or various planets, which can then help us explain how planets form, and of course help us figure out a little bit more about the solar system and the formation of planet Earth. And one of the ways scientists have been trying to achieve this is by looking for evidence of a sudden increase in various types of dust in the early planetary system, and by trying to find these various debris clouds, which in theory can only be produced if something really large smashes into something else very large. And most of this done using various infrared telescopes, such as the iconic, although now retired, NASA's Spitzer Space Telescope, that for a very long time has actually been conducting a lot of different surveys and looking at a lot of distant stars. In the process, detecting at least several events that suggested something, such as maybe asteroids, was definitely hitting other objects in various star systems. One of the first such examples was actually from back in 2014, where there was a clear sign of something increasing the infrared brightness in a distant star system, with the only explanation for the sudden increase in brightening, specifically the infrared brightening, essentially being a sudden introduction of a lot of dust into that particular star system. But now, 8 years later, the same team, using a very similar technique, was able to identify something else even more interesting. Not only were they able to see the brightening effect, but they were also able to see the passage of this relatively large dust cloud pretty much right in front of the star, the event that we usually refer to as the transit event. With the transit, or the dimming due to the transit, then allowing the scientists to determine what exactly very likely created all of this dust. Thus allowing the scientists to calculate the size of original objects and even see in relatively real time how all of this evolved over time and what all of this created at the end. So first of all, this particular study looked at approximately 100 observations between the year 2015 and 2019. And so while observing this particular star system for roughly around 4 years using infrared light, the scientists were able to, first of all, once again detect the sudden increase in brightness, which in this case started around the middle of 2018, and which also indicated to the scientists that there was a sudden increase in activity, very likely an increase in collisions. But around the same time, as the telescopes, both in space and on planet Earth, were looking at the star, they also detected the transit coming from the star itself. And based on the star's parameters and the observations coming from the system, the scientists were able to work out that this wasn't just any type of a transit, this was not a planet, but instead represented a definitive sign of a debris cloud that was basically blocking the star, which, when combined with the infrared observations, allowed the scientists to work out exactly what collided with what, and even figure out the approximate shape of the cloud that was produced. And according to these initial observations, the cloud was very likely extremely elongated and at least 3 times the size of the star. But by observing the brightening using Spitzer telescope, it became more apparent that the debris in this case spread over a much larger area, at least 100 times the size of the star, which would of course indicate a tremendously large cloud and a huge amount of dust that was generated by this collision. In this case, at least 2 relatively large planetesimals, for example similar in size to the famous Vesta located in the asteroid belt, would have to collide at a relatively high speed. Now this would be a collision between 2 objects a few hundred kilometers in size, and based on the orbital observations, these objects would be about 0.6 astronomical units away from the star, which is roughly the same distance as Venus is from the Sun. But because this was very likely an extremely high-speed collision, and because in this place around the star the velocity of each of the objects would be around 50 kilometers per second, this would actually be a very high energy collision, producing a lot of materials, producing a lot of dust, and evaporating a lot of material as well. And all of this evaporation and all of the tiny particles produced by this collision would then result in a kind of a impact chain reaction where objects will start colliding with other objects and produce even more dust. But over a period of several months, the scientists observed a sudden decrease in brightness, with the dust cloud eventually becoming more transparent and more translucent. And within just a year, most of the dust that basically made the star brighter in the infrared light became more or less invisible. But interestingly enough, follow-up observations from Spitzer telescope indicated that at least double amount of microdust was now present in the entire system, which of course makes this extremely intriguing and potentially raises quite a lot of questions as well. And because this star system in this case is slightly larger and more massive than the solar system, it also presents a pretty good opportunity to see how exactly various types of stars evolve and how certain types of planets come to be as well. Which is of course a really important step in trying to help us understand how various terrestrial planets form and how various star systems eventually create the structure that we detect around the galaxy. In other words, this particular star system is actually one of the most important when it comes to understanding how early star systems evolve. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries in regards to how various very massive planets can actually influence the evolution of stars, and more specifically can actually influence their age or some of the age-related properties, making certain stars appear much younger than they actually are, or possibly even having them act much younger or become more active. Something that seems to be directly connected to the discovery of various hot Jupiters. Very massive planets, very often extremely close to their parent stars, which by themselves are already strange planets, but they also seem to have very strange effects on the star itself. And so let's discuss this in a little bit more detail, talk a little bit more about how scientists discovered this, and what it actually means for our understanding of star evolution. But let's actually start with the idea of star age and star evolution first. So today we understand that as stars form initially, they acquire a lot of the rotation and a lot of spin from these early molecular clouds. Early stars, young stars, will usually spin really fast. But different types of stars, and stars of different mass, will usually spin around a relatively similar velocity. For example, for a typical Sun-like star, the average velocity is usually around 12 kilometers per second. That's the velocity on the equator. But more massive or more active stars will often have higher velocities. Actually, some of the most active stars and even more massive stars, such as Achernar that you see right here, can spin ridiculously fast. This one spins at approximately 85% of its limit before it falls apart completely. As a result, it has this unusual egg shape. But a few decades ago, scientists like Andrew Skumanich realized that there is a pattern here and proposed something that we refer to as gyrochronology. The idea that there is actually a relationship between the speed of the rotation of the star and their age. And by measuring various temperatures of stars, determining their type, and also discovering their rotation, it becomes possible to work out the age of a star just by looking at how fast it spins and what type of a star it is. And there have been quite a lot of studies out there in the last few decades that created these beautiful graphs that essentially allow us to see the age, the rotation period, the effective temperature of the star, creating a very effective way for determining how old a star might be just by looking at how fast it spins. But why exactly would that matter? Why does the speed relate to the age? Well, the principle is really simple. The stars, as they age, actually rotate slower and slower. And the reason for this is pretty simple. Stars produce magnetic fields. More powerful, more active stars produce more magnetic field. The ones that spin faster produce it even more. And certain stars are going to have super strong magnetic field as well. At the same time, stars also all produce stellar wind and emit a lot of gas from the surface of the star itself. Here's some of the more extreme examples of this. And stellar wind contains quite a lot of ionized gas that's influenced by the magnetic fields as well. And essentially what this creates is a kind of a mechanism where the magnetic field from the star itself starts to hold on to or starts to pull at the stellar wind. But because the star is also rotating, it kind of slowly starts to slow down the rotation of the star. It doesn't obviously happen right away, it takes millions and actually billions of years. But with time, the star starts to spin slower and slower because of this interaction between the magnetic fields and the solar wind, or stellar wind. And so if we find a bunch of G-type stars of the same temperature, we'll discover that some of them will be spinning slower and will be much older in age, whereas the ones spinning faster are probably extremely young. And by mixing this with certain other observations and certain other properties, such as chemical properties, and combining this with the iconic HR diagram, also known as Hertzsprung-Russell diagram, that allows us to predict the age of the star based on the temperature and the mass, it then becomes possible to combine this in determining the age for quite a lot of different stars. And that of course includes stars with various planets. It's obviously still difficult and still kind of challenging to know the exact age, but by combining these various observations, it does become possible. Gyrochronology though, or the rotation of stars, always played a really important role in all of this. And in case you're wondering how the scientists discovered the rotation of different stars, it's essentially by looking at various features that seem to come into view once in a while, for example different sunspots or various powerful emissions. But the scientists wanted to find out if any of this changes if there is a giant planet in orbit very close to the star itself. Do these planets actually do anything to the star to, for example, make them spin differently, or to possibly make them appear younger or even be younger, or essentially changing the lifespan of a typical star? And in this case, the best way of looking at this is by using hot Jupiters, the planets extremely close to parent stars, and then maybe comparing this to some other stars that, for example, might have nothing around them. Here's one of the more iconic objects right here, known as WASP-12b. Now you can see that it does orbit really close to the star, and because of this it actually does produce certain effects somewhere on the closer side right here. Some of these effects have previously been observed before, including of course slightly more activity on the side of the star where the planet is currently located. But it doesn't seem to be the only effect these planets have. And the thing is, when some of the first exoplanets were discovered, which happened to be hot Jupiters, some of these early discoveries appeared to be around really young stars. In other words, for some reason, if there was a hot Jupiter around a star, the star seemed to be acting much younger. Now, to some scientists, this implied that maybe these objects only exist in very young star systems, and as star systems age, and as essentially they evolve over time, maybe these hot Jupiters just fall into the stars and disappear completely. This also kind of implied that maybe one of these planets used to exist in the solar system and had the same fate. But there could be actually a completely different explanation, and this recent study, that as always you can find in the description below, makes a very strong argument for this. And in this case, the scientists decided to focus on various binary star systems, with at least one star possessing some kind of a hot Jupiter, but the other one not possessing anything, or at least nothing we've discovered so far. The reason why scientists decided to choose binary systems is kind of similar to why in medicine a lot of scientists use twin studies. By comparing the twins, you can actually learn if something has an effect on a person, if for example they're given different medicines, or if they're raised in different conditions. In this case though, it's kind of assumed that both stars were born in very similar conditions, and so their initial rotation speed would probably be around the same because they would receive relatively similar angular momentum from the initial molecular cloud. And here they've examined 16 separate binary star systems, with every one of them having one star with a hot Jupiter, but the other star not having any companions. And as you can imagine, their findings were really surprising. In every single case, the star that had a companion appeared or looked much younger. It was spinning much faster and was producing a lot more emissions, naturally suggesting that they had faster orbital period or faster spin. And to the scientists behind this paper, it implied that somehow the hot Jupiter in this case transfers some of the angular momentum to the star, most likely via some kind of a tidal force, which of course affects the rotation of the planet, but more importantly affects the rotation of the star as well, and affects it by increasing its rotation speed and also increasing the activity on the surface. Although intriguingly, unlike for example the Earth-Moon system, where the Moon is slowing down planet Earth by orbiting around it, in this case this was the opposite effect. As the planet orbits the star, it seems to increase its rotation. Although it does actually kind of make sense. For the Earth-Moon system, Moon has always orbited around the planet much slower than the rotational spin of planet Earth, and so over time it started to slow down our planet. But in case of these hot Jupiters, the orbital period here is much faster than the rotation of the star, and so it basically causes them to spin up. Naturally, if they orbit much farther away and thus orbit slower, it would not have the same effect and possibly even would have the opposite effect. And as a result, this seems to create a lot of activity on the surface of the star, including more X-ray activity, and by association very likely more solar wind as well. And because the star is more active, it very likely ages very differently from its partners as well. Because they have more emissions from the surface and lose a lot more hydrogen in the process, chances are they actually might live much longer as well. Usually stars of lower mass have much longer lives. Although at the moment that's just a guess. It's still unclear what exact effects this would have on a star, and it would be quite difficult to determine this unless we actually have a huge sample of these objects where the scientists can actually create some kind of a diagram to determine all of this. And more intriguingly, the scientists in the study also discovered that stars that had smaller planets, so basically planets that are terrestrial, or planets that are extremely far away from the star itself, appeared much older, much dimmer, and much calmer, suggesting almost the opposite effect from smaller objects. But the exact effects are not clear just yet. And so only objects that are much larger and much more massive and orbit much closer seem to actually have extreme effects on stars, which at the moment really creates more of a problem than a solution. It means that predicting the age of these stars would be practically impossible, unless, like in this case, they actually have a twin where there are no planets, where the age can be determined much easier. And so I guess the next question would be, well, maybe by measuring the differences in the appearance of age of these twins, some of the future studies can determine if there is maybe a formula or a relationship that can help us understand the exact effects these planets have on stars, allowing the scientists to quantify them directly. Hello wonderful person, this is Anton, and this right here is a simulation of what Proxima Centauri b, the nearest exoplanet to us, might sort of look like. But it's a simulation based on our perception of what terrestrial planets might be like somewhere out there. In a lot of recent papers though, we've discovered that, well, we might be a little bit too optimistic in how we imagine a lot of these terrestrial planets. They might look entirely different from planet Earth, and they also might have extremely different properties both inside of them and on their surface. And today we're going to be discussing this new, relatively recent study that essentially presents a new idea about these new planets that the scientists believe exist out there. Terrestrial planets, but they refer to them as the Eggshell planets. Or I guess to be more scientific, brittle lithosphere planets. The planets whose surface is literally breakable, kind of like a typical eggshell. And so I wanted to discuss this new idea and new proposition, and also focus on the idea of a lot of these terrestrial planets we've found so far being way more exotic than we can even imagine right now. Something that relates to another video I made that should be popping up somewhere right there at some point. And the proposition itself is really not far-fetched at all. As a matter of fact, when we look around at planets like Mars, Venus, and Earth, we realize that even though these three planets are already quite different from one another, generally they do contain relatively similar elements, or specifically relatively similar minerals on the inside. For example, they all seem to contain quite a lot of olivine, the green mineral that makes a huge part of the crust and also makes a big part of the mantle and transforms to some other minerals as well. It's also one of the reasons why our planet has so much water. Olivine and its derivatives are really good at maintaining and sort of keeping water on the inside and releasing it with time. And so minerals are a really important and somewhat essential concept when it comes to studying exoplanets and trying to understand what goes on those planets and how those various planets could be different from planet Earth and even planets like Mars and Venus. And this is a really important feature to investigate because we usually assume that a planet can be habitable if it's just a certain distance away from its parent star and if it has a chance to potentially have liquid water. But what we don't really consider is the fact that liquid water does not just come from a distance from the star. The liquid water and habitability is also formed by a lot of geologic activity on the planet. And more importantly, what the crust is actually made out of is extremely important for potentially habitable exoplanets. So for example, in order for us to find another planet like Earth, it really has to have so many different features extremely similar to planet Earth. So not just being in a habitable zone and having water, but also having just the right composition, just the right structure, and just the right mass and gravity in order to maintain a lot of this balance and to produce stable habitable conditions on the surface. One of the videos I made previously also discusses what's known as the stellar archaeology, the discovery coming from a lot of different white dwarfs that essentially swallowed their planets that used to orbit around the stars that used to exist here, that suggests that a lot of these terrestrial planets were extremely different from planet Earth and possessed conditions that we can't even imagine, even though many of them were very similar in mass and possibly even in the position in the star system compared to planet Earth. So this is a really important discovery, and this once again highlights the importance of studying the geology of various planets. And when it comes to some unusual geology, one such proposition comes from this recent paper, the existence of eggshell planets. Planets that, like eggs, have extremely flat surface and also have extremely brittle surface that very likely breaks very easily. Planets that also create conditions that would be almost impossible for life to survive on. A lot of these planets would be very likely uninhabitable. And all of this is mostly because of the lithosphere and specifically the upper crust of the planet that's essentially one single piece, kind of similar to an eggshell. And in this case, there are no plate tectonics, there are no continents, there are no mountains, no volcanoes, no major geologic components. I guess in some sense, you could literally call this flat Earth. But in this case, it's really flat because of the geology and because of the way these worlds are created. And because the entire crust on top is just one single piece. The piece that doesn't allow for any major topography to exist here. And not having plate tectonics, or essentially not having any sort of geological activity on the surface, already prevents this type of a planet from having a lot of different cycles like planet Earth. A good example of what happens when planets have no plate tectonics and have no actual cycles are planets like Venus. Eventually they become just way too extreme for anything to survive. And interestingly enough, Venus actually has some properties on the surface to suggest that it could also be seen as a kind of an actual planet, but only in some parts. It does have certain lowlands that are completely flat and also have an extremely thin and somewhat brittle surface which can break if something hits it. So Venus is actually one of the better examples to try to study this. But even Venus in this case is a lot less brittle. It actually is not an actual planet in that sense. And so in order to understand what exactly happens to these planets and how such planets can form, the scientists in this paper ran thousands of different models and simulations, changing various parameters such as the gravity, the age of the actual planet, the temperature on the surface, the temperature inside the planet, changing a lot of other parameters in order to see what sort of planets will be produced in certain conditions. But in this case, they really focused on a planet extremely similar to planet Earth, both in mass and of course in size, which is what we usually call an Earth-like planet. And so by changing various parameters such as distance from the host star, the internal temperature, composition, age, they started to produce various models with different thickness of the crust itself, the thickness of the lithosphere. And as I mentioned before, lithosphere determines an extremely important factor in determining habitability of a planet. For example, the movement of various plates, such as the subduction plates, recycles a lot of various gases and a lot of different materials in the Earth atmosphere. One good example here would be the CO2 gas that sort of gets trapped in all of this rock, then slowly makes its way lower and lower into the mantle, and eventually gets released with a lot of volcanic eruptions. But it's not just CO2, it's a lot of other gases as well. But to even have volcanoes like this one right here, or to have subduction, or really any kind of plate tectonics, you have to have a certain strength of the lithosphere. The crust has to be not brittle enough and not thick enough. So kind of like what we have on planet Earth. But according to their model, once they simulated a lot of these planets, many of them turn out to be very different from planet Earth. And specifically, many of them turn out to be these actual planets. Very brittle surface that's easy to break with even a single impact, and practically nothing geological on the surface, completely flat terrain. With one major factor playing the most important role, the surface temperature. And in this case, planets that would be much smaller but also a little bit older than other planets would usually have very thick but brittle lithospheres. In this case, it's somewhat similar to what we have on Mercury and what we have on Mars, which is also why neither of these planets can have habitable conditions long term. But then some larger, younger planets, in this case something we usually refer to as a super-Earth, would have very thin brittle lithospheres. And in this case, the only comparison we have from the solar system come from Venus as well. It's certain parts of lowlands on Venus that are just extremely flat and also very thin in thickness. And if Venus did not have a thick atmosphere, a single strike from a single meteorite would completely shatter the surface here. And then depending on certain combinations, you can have extremely brittle layers, whose surface might resemble something like this, flat but full of cracks everywhere. And certain parameters produced extreme lithospheres on the surface. In this case, it was usually a super-Earth, extremely young, relatively close to the star, and also containing a lot of radioactive materials inside of it, which to some extent could also be described as Venus. Although Venus is probably one of the milder cases of these types of planets. And so when it comes to studying exoplanets, it's really studies like this that allow us to understand that just the position and I guess the temperature on the surface is really not everything for the planet's habitability. A lot of things here will depend on the actual rocks on the inside, on the actual temperature on the surface, and more importantly on the types of minerals present inside. And so this study, that as always you can find in the description below, presents a really important first step in trying to identify important properties for the future studies of exoplanets and exoplanets that could be potentially habitable. And here we're talking about being habitable for millions and billions of years, for basically life to develop and potentially survive. And in the paper, the scientists have also identified several planets that we've discovered in some of the previous surveys, and here we're talking about this planet, this one here, and a few other ones, that seem to be actually these unusual planets with extremely thin lithospheres. Possibly even as thin as 1 kilometer. And that's really because of the temperatures on the surface and because of their position in the star system. With some other planets, even the ones in the habitable zone of their stars, being on the opposite spectrum, extremely thick lithospheres. Which once again suggests that just finding a terrestrial planet somewhere out there doesn't really mean much. We still have to understand what happens on its surface, we still have to understand the geology and the composition of the minerals, and we still have to know more about the planet by finding different ways to study what happens on the actual surface and how the crust, the atmosphere, and a lot of other interaction here might potentially influence the habitability or create a planet with extremely unpredictable and somewhat brittle surface, which once again suggests that planet Earth seems to be just that one lucky planet. At least that's what we get from a lot of these studies. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries coming from white dwarfs that help the scientists answer a really interesting question. What exactly are some of the other terrestrial planets made out of? And the answer to this question is quite surprising. Turns out that a lot of planets out there are extremely exotic. So let's discuss this particular discovery in more detail, starting with the idea of terrestrial planets themselves. One of the bigger questions today is, of course, are planets in other star systems going to be relatively similar to what we have here in the solar system, at least in terms of the composition and in terms of the structure? So for example, if we take a look at the iconic TRAPPIST-1 system, and if we take a look at the terrestrial planets discovered here, are we going to be discovering planets with relatively similar minerals and composition, or are they going to be entirely different and something that we can't even imagine right now? And considering that the scientists have already discovered several thousand different planets out there, with many of them being terrestrial, this of course presents a very intriguing mystery that needs to be solved, especially if we want to find out more about potential extraterrestrial life or even extraterrestrial intelligence living somewhere out there. But because of the way that we find these planets, usually by looking at shadows or by looking at various interaction with the star, it's generally difficult to know exactly what these planets are made out of. However, there is at least one way the scientists are aware of. And it's actually called archaeology, specifically stellar archaeology. There's a way to study the leftovers of different planets by looking at specific star systems, and then by studying what these leftovers are, we can maybe determine what these planets used to be made out of. In other words, instead of looking at existing planets, we can hypothetically look at some of the planets that used to exist and then sort of extrapolate some of the findings based on that. And one of the best known ways to do this is by actually studying the atmospheres of the multiple white dwarfs we've discovered in the last few decades. White dwarfs, as you might already know, are essentially the end product for a lot of different stars, including our Sun. It's also going to become a white dwarf in the next few billions of years. And once the star becomes a white dwarf, it's going to stay a white dwarf for billions and even trillions of years. And during that time, because of various gravitational interactions, it's slowly going to absorb a lot of the matter orbiting around it. And here we're talking about things like asteroids, space dust, and of course the leftovers from various planets, or even planets themselves. And so a lot of these leftovers from various objects are going to eventually end up on the surface of the white dwarf itself, thus contaminating some of its atmosphere. And because white dwarfs generally still emit quite a lot of light that we can then process using modern techniques, by looking at what this light passes through and by seeing what spectra of light are being absorbed and what spectra of light pass through the atmosphere, allows the scientists to establish specifically what elements and what components are present in the atmosphere of these white dwarfs. Which then, in effect, helps them understand what this star system might have had in terms of decomposition and what some of the planets might have been made out of. So this is why this is generally called stellar archaeology, although it obviously has other names as well. And so the scientists behind this recent paper, you can find in the description below, decided to take a look at 23 well-known polluted white dwarfs, or white dwarfs with a lot of different components in their atmosphere, with all of them located within about 650 light-years away from the solar system. And in this case, they focused on the white dwarfs where a lot of the things have already been measured by a lot of different observatories, with things like magnesium, iron, silicon, and calcium already previously detected and measured in a lot of these objects. But just finding these elements is not enough. The scientists still have to try to reconstruct what sort of potential minerals could form from all of these elements to then create the planet itself. For example, if we take our own planet, planet Earth, if we were to somehow identify just the elements present inside the planet, we're going to discover that for the most part this is all silicon, iron, magnesium, aluminium, and oxygen. Similar to the stuff discovered in those white dwarfs. But each of those elements in turn then forms various very specific minerals, each of them having very specific properties. As a matter of fact, the properties of these minerals is what makes planet Earth so unique. And for Earth, a lot of these elements form two major minerals. The mineral known as olivine that contains magnesium, iron, silicon, and oxygen, and the mineral known as pyroxene that contains silicon, aluminium, oxygen, and sometimes sodium, iron, and magnesium, and a few other elements. And so in other words, the minerals or the production of these minerals is actually essential to the planet itself. For example, some of these minerals are going to be able to dissolve much more water, and so the planet might not be as wet in a sense. Whereas some other minerals, if they're developed in a certain way, they might be extremely strong and thus prevent any plate tectonics and the development of various cycles that are essential for the planet and for the establishment of life. On the other hand, if the actual minerals are very weak, they might result in some extreme plate tectonics, and the effects of this are obviously not known to us. And so when analyzing the white dwarfs that they were looking at, they have actually discovered something a little bit more unusual. They've discovered that a lot of these white dwarfs had a much bigger variety of different compositions possible than any of the planets we have here in the solar system, including some of the more extreme planets like Venus. Which also suggests that a lot of these planets in these other star systems might have had extremely different minerals and a lot of different rock composition that's just not present or even imaginable here on planet Earth. And some of these rocks and some of these unusual compositions were so extreme that the scientists even had to create special names for them. One of the examples here is quartz pyroxenites, also periclase dunites. So these would be some extremely new types of rocks that would exist on these distant planets or have existed in the past, but are definitely not present anywhere in the solar system. And by definition, this would make all of these terrestrial planets that existed around these white dwarfs exotic. Which means that they would be very difficult to imagine, very difficult for us to understand, and their properties would be extremely difficult to establish since we have no idea what these minerals are like and what sort of properties they have on those planets. So for example, if one of these planets had a mineral with much lower melting point, it might actually look something like this. It would end up having extremely thick crust that would be practically unbreakable. And so in a sense, the conditions on these planets would be maybe similar to what we have on Venus, where we don't have any plate tectonics or any interaction on the surface. But here even volcanoes might be extremely rare because of the thickness and the strength of the crust. And according to the scientists, even some of the previous studies were able to discover certain elements that seem to be present in, for example, Earth crust specifically, but a lot of these elements are very minor, they're not actually that important. They don't really form the majority of the minerals. And so instead, by measuring the major elements, such as for example silicon, and then by measuring the amount of various elements present, it may become possible to work out what sort of minerals these planets were made out of. Also interestingly, in a lot of these white dwarfs, the majority of the elements discovered were magnesium and not silicon. And to the scientists behind this paper, this means that a lot of the material that was essentially swallowed by the white dwarfs very likely came from within the planets themselves, not so much the outside part, not the crust or the atmosphere. In other words, what we're probably looking at here are the leftovers of different mantles of different terrestrial planets. And this is a bit intriguing because in this case the scientists even suggest that none of these white dwarfs seem to contain the crust of the planets, which means that either these planets never had any crust, or the crust was somehow removed before the planets collided with the white dwarf. But having no evidence of this crust, or basically the surface of the planet, is a little bit intriguing. Although one obvious explanation here is of course that maybe crust just represents a very small fraction of the entire planet, and so it's just not visible in these observations. But the most exciting part of the discovery in this case is really just the different proportions of different elements discovered in these white dwarfs. Which of course implies that a lot of these planets, despite being terrestrial, are extremely different from any of the planets in the solar system, and might have extremely different properties and thus ability to, for example, sustain life. Which could also be another important keyhole for the existence of, for example, extraterrestrial life. Maybe Earth once again got super lucky. It just happened to have the right composition of the right minerals to create the right conditions. To create the conditions, for example, for extremely active plate tectonics, very large ocean that covers most of the planet, and most importantly, the cycle that lasts for billions of years. So maybe for the planet to look like this and to be somewhat similar to planet Earth, it does need to have these very specific minerals that are present on planet Earth as well. And maybe a lot of these other exotic planets look and behave in a very different manner. Which once again could be one of these potential explanations why we're not hearing any other aliens out there. Maybe their planets are just not good enough. Hello wonderful person, this is Anton, and today we're going to be discussing a recent discovery of essentially more exoplanets. But these exoplanets were discovered using a very unique and extremely interesting method. They were discovered by listening to radio emissions. Something that was only done once before, approximately a year ago. And so in this particular case, this here is a continuation of that study that allowed the scientists to discover a lot more of these exoplanets that very likely exist around different stars. Or in other words, it looks like we've discovered a new method of finding exoplanets. So let's start right here. This is one of my most favorite pages that illustrates how we usually find various exoplanets and how we've discovered most of them already. You probably already know that the transit method, or essentially looking at the shadow of a planet as it passes in front of the star, is the most successful method to date. And a lot of other successful methods today usually use some sort of a visual observation when the star does something, like for example, maybe it wobbles around, which usually implies some sort of a massive planet in its orbit. Maybe the star increases in brightness very briefly, indicating some sort of a gravitational microlens. Or maybe we can actually cover the star completely and see the planet next to it. So all of these methods have successfully been used in the past, but sometimes the scientists discover a completely new method, something that was either only theoretical or something that was actually never thought of before. And since a typical star emits a lot of different frequencies from its surface, and since only some of these frequencies have been thoroughly studied, there are definitely still a lot of different things we can do with a star in order to possibly find planets around it. And since modern instruments are so much better at detecting various frequencies, and looking at the night skies in anything from the radio waves to gamma rays, today the scientists have so many different methods that could potentially be used to discover new planets or some other mysteries around different stars. And one of the questions that some of the scientists asked a few years ago is, can we actually detect some sort of a frequency that either forms by the star interacting with the planet or comes from the planet itself? And one of the reasons they asked this question is because something similar was detected coming from Jupiter a few decades ago. Back then, the scientists discovered that Jupiter was emitting unusual radio waves that were extremely difficult to explain, and it took a few decades to finally figure out what's happening here. A lot of this is actually caused by the closest moon to Jupiter, known as Io. Io is volcanic, and so as it emits a lot of the gas from the surface, some of this gas turns into ions and becomes charged. a lot of this charged stuff then starts interacting with the Jupiter's magnetic field. And because of this interaction, some of these charged particles then start moving along the magnetic lines of Jupiter and produce a lot of radio waves that culminate in an extremely powerful emission right close to its aurora. And so the aurora of Jupiter right here end up producing extremely powerful radio emissions that in theory could be visible even from other star systems. And just over a year ago, we've discussed one of these first discoveries. And so by applying this idea, the scientists used the European LOFAR, also known as the Low Frequency Array, represented by all of these different observatories across Europe, to detect radio emissions from the object known as GJ 1151. One of the older videos right there discusses this in more detail. Now this object very likely contains a planet that seems to interact with the parent star. Or in other words, just like Jupiter and Io, in this case it's the star and the planet. And one of the reasons this seems to actually work is because of the size of these star systems we're looking at. All of these star systems are red dwarf systems, kind of similar to TRAPPIST-1 right here. And here's how TRAPPIST-1 compares to the Jupiter system with its moons. Because some of these planets are going to be really massive and some of them are going to be really close to the parent star, and because some of them will also be volcanic or possibly produce ions in some other way, many of these planets will produce very similar effects on the surface of the star to what Io produces on the surface of Jupiter. But one of the major reasons why this works so well is because of the type of the star we're looking at. These are red dwarfs. They're extremely magnetic and they also produce a lot of different stellar flares, and thus naturally produce a lot of radio emissions already. With the magnetic field of a lot of these stars being so powerful that it definitely envelops some of these planets. And so by using the world's most powerful radio telescope known as Astron, the scientists were able to identify 19 different signals from 19 different red dwarfs that are quite well known to us, the ones you see in the list right here. All of them investigated in a relatively low frequency of 144 MHz, with 4 of the objects showing emissions that could be best explained if there was a planet around them. But we cannot certainly say that these are planets and that all of this is caused by planets, and the scientists wanted to confirm that they exist using other methods. Unfortunately, at the moment, they were not able to identify these planets using any other means. This doesn't mean they don't exist though, it just means that they're not massive enough and not large enough to be noticeable using other methods. Which in some sense is even more exciting. It means that these radio observations could potentially provide an even more sensitive way for us to find various planets that could be hidden otherwise. Or in other words, even though it could be maybe some other phenomenon that's producing these particular observations, if these are planets, we might have just found an extremely accurate way of finding planets, even if these planets are tiny and would be invisible to a typical optical telescope. And so the initial findings suggest that if these planets do exist, they are probably not more massive than planet Earth, but they could still be less massive, and we've actually found a lot of these planets around other red dwarfs already. And one of the reasons the scientists in the study actually believe that this is coming from planets is really because of the similarities with Jupiter and Io. The emissions are very similar to what we see in this system right here. And so it's actually quite likely that these planets are real and that we're going to be able to identify them using some other telescopes, such as maybe the James Webb telescope that's going to become operational later this year. And so all of this of course implies that we could in theory use LOFAR and Astron to detect a lot of various planets around nearby red dwarfs, and there are quite a lot of red dwarfs near us. But the problem is that the sensitivity of the telescope ends at about 165 light years away from planet Earth. And so this particular technique is only useful for some of the nearby red dwarfs. Anything farther has to be done in some other way. And if the scientists in this paper are correct, and if this is confirmed in future studies, this is a huge groundbreaking step for the radio astronomy. It means that the future radio maps, like the one you see right here, are not just going to be black holes and distant galaxies, or things like supernova remnants you see right here. It's also going to be a lot of hidden planets. Planets interacting with their parent stars and producing very specific radio emissions. And so a lot of these new advances are actually because of the advances in radio astronomy. New telescopes afford us ability to see things we could actually never see before. Which is also why so many new mysterious discoveries such as orcs or fast radio bursts have only been made in the last decade or so. We've only made all of these discoveries because of the advances in radio astronomy. And interestingly enough, even some of the really old magnetically inactive stars ended up producing emissions that were visible with the telescope, which means that we've reached a completely new sensitivity level when it comes to radio astronomy. As a matter of fact, the scientists speculate that by looking at magnetically inactive red dwarfs and by seeing emissions coming from their surface, we'll be a lot more likely to discover even more planets, simply because there's really no other explanation for what we're seeing here. These emissions can only be explained if the star has just a little bit of magnetic field and the planet is somehow producing charged particles which then create a lot of these radio waves, in the same way that is done around Jupiter and Io. And so by focusing on some of these slowest rotating or essentially magnetically inactive stars, it's very likely that in the next few years we'll discover a lot of these hidden planets. But until we do, that's all I wanted to mention in this video. There is something really mysterious about an idea of a lost planet. A planet that might have existed somewhere in, for example, our solar system, and then for one reason or another became lost because of the gravitational interactions with other objects. And it looks like today we're actually going to be talking about some of the new discoveries, very groundbreaking discoveries, in regards to these lost planets. Hello wonderful person, this is Anton. Today we're discussing rogue planets, also known as planemos, or simply FFPs, free floating planets. An actual scientific concept that's still quite mysterious because, well, they're obviously extremely difficult to find. But despite of this, one team seemed to have persevered and discovered a tremendously large amount of these rogue planets in a relatively nearby star-forming region of space, with pretty much all of them being visible in this image right here, provided by the European Southern Observatory. And so let's actually discuss exactly what this represents, how these planets were found, and what this means for the future of astronomy. But also let's start maybe right here in Space Engine. So based on the previous assumptions about how many rogue planets we expect around the solar system or in a typical volume of space, here we can actually even try to find some using procedural generation. So for example, within approximately 10 light years away from us, this software expects us to find 3 different rogue planets, with one being right here. And that's basically the reason why they're so difficult to find. They produce nearly no light at all. It's maybe a little bit easier to see this if I sort of make other stars a little bit more visible, so you can at least see its shadow. And so in a nutshell, that's basically the problem with finding rogue planets. We know they're there, a few of them have already been discovered, but because they produce no light and because they're also not really massive to have a lot of other effects, in the last 2 decades only a handful of them has actually been discovered, and most of these are not even possibly rogue planets. A lot of them might be either brown dwarfs, or basically slightly more massive objects, or maybe even red dwarfs, actual stars. And so with a lot of these examples you see here, there are still candidates, they're not even confirmed. But since a lot of theories regarding the formation of the solar system predict the existence of at least one more planet that probably existed here, but was basically kicked out in the early formation of the solar system, in the last decade or so, a lot of scientists have been trying to find new ways to find these planets, because we're hoping to maybe even discover some of these hidden planets that probably existed in the early solar system, that are now obviously traveling somewhere across interstellar space completely by themselves. More importantly, this might also help us find the mysterious Planet 9 as well. But in reality, their origin and their nature is still very poorly understood. For example, from the planets discovered so far, some scientists think that maybe they were actually produced completely by themselves alone, meaning that no star was actually responsible for their formation, and some of them might have actually been formed in some other way. And up until this point, or up until this study, not that many were known to begin with. For example, one of the most likely nearest such objects to us is this one right here. It's located roughly around 7 light years away from us and is most likely some sort of a really massive Jupiter-like object, or possibly a somewhat less massive brown dwarf. But it's definitely some sort of a rogue object, so basically a rogue planet. But this new study now might have actually discovered roughly around 70 to maybe about 170 new rogue objects, with the majority of them very likely being free-floating planets. But why is the number so uncertain? Why is it 70 to 170? Well, as the study, that as always you can find in the description below, explains, it's really because of the way these objects were discovered and the way that they were measured in general. So first of all, in terms of the actual structure and mass, it's expected that many of these planets would probably resemble a planet like Jupiter. Many of them are probably a little bit more massive. And to discover these objects, the scientists behind this paper mostly focused on the region right here between Scorpius and Ophiuchus constellations, mostly looking at various star-forming clouds or star-forming regions that are normally responsible for obviously creating stars and planets. But in this case, all of the data came from roughly around 20 years of observations from a variety of both ground-based and space-based telescopes that essentially focus on measuring both the motion of stars across space, but also their luminosity and their color, with the telescopes then providing data for millions of different objects, and the data here being basically luminosity and the motion across the night skies. But the majority of the important data came from the infrared telescopes located in Chile, part of the European Southern Observatory. And that's actually the main way to look for these very difficult to otherwise see objects. They only produce light in the infrared. As you probably know, your body right now is also producing light in the infrared. And that's because both your body and a lot of these planets have a relatively similar temperature, at least on the outside. Inside they might be actually much hotter, and they probably are much hotter, but the stuff we see from the outside is usually in the range of about 200 to maybe 400 Kelvin. And so by combining the extremely accurate motion data from the Gaia telescope along with the infrared data from a lot of these other telescopes, the team was able to identify which of these objects were most likely not stars and were very likely planets. But the thing is, because of the way that all of this was measured, it's currently impossible for them to measure the actual mass of these objects. They can only measure their brightness and their potential temperature. And so because of this, it's not entirely certain which of these objects are actual rogue planets and which of them could still be maybe brown dwarfs. Normally when it comes to defining brown dwarfs, at a mass of about 13 masses of Jupiter, we generally consider this to be now a brown dwarf and not a free-floating planet. So basically a somewhat different type of an object. You can learn more about this in some of the previous videos. But in order to establish which of these were planets, the scientists had to basically rely on a slightly older technique. They relied on measuring the brightness of these objects, with the general principle being that, well, if you have an old planet, it probably had a longer time to cool down and thus will probably produce slightly less luminosity. And so here, by looking at a certain region and identifying its average age, they might actually be able to predict the age of an object and compare it to its actual brightness. So for example, discovering a bright object in a relatively old region suggests that it's probably a brown dwarf and not a planet, with some of the dimmer objects obviously being rogue planets. And because of this, there is a bit of an uncertainty in the discovery of these objects. There are roughly around 170 of them in total, but only 70 of them appear to be certainly rogue planets, with the 100 other objects maybe being brown dwarfs, but still interesting objects nevertheless. And as the scientists mentioned in the paper, this was really surprising. The sheer number of these objects in such a small region of space is unexpected. And this presents, I guess, a mystery and also an opportunity to try to figure out how all of this works and how these objects are created. At the moment, this is definitely beyond our original predictions. And this is why I actually started with the simulation showing us that there are only about 3 objects expected in the vicinity of planet Earth. Specifically, the scientists here suggest that there are at least 7 times more rogue planets in the vicinity than we originally anticipated. And so within approximately 10 light years away from planet Earth, we might expect maybe 20, maybe even more. Which also implies that some of these objects might be formed in ways we cannot currently explain. So at the moment, the scientists think that some of these objects could be created by themselves just from the natural formation from the original clouds. But only some of them and only a small fraction of these objects are formed this way. Many of them are probably kicked out of various star systems. And based on the sheer number discovered, this paper makes an implication that actually a huge number of these planets are coming from other star systems, and so the process of kicking out planets from stars seems to be very common. With all of this most likely happening within just the first 10 million years of the formation of a typical star system. And that is actually a really interesting discovery and potentially will lead to new techniques and new ways to discover these objects in the near vicinity. Now, if you remember, especially if you've been following astronomy for quite a while now, we didn't actually even know that brown dwarfs were that common up until I guess about 8 years ago. And so a lot of these surprising discoveries in regards to brown dwarfs and rogue planets are all somewhat new to us. But more importantly, there are going to be so many more discovered in the next few years for one single reason. Remember how I mentioned that you can only see these objects really well in the infrared? Well, it just so happens that we have a very powerful infrared telescope being launched in just about a couple of days from when I'm making this video, which means that it's already in space when you're watching this video in the future. The world's most powerful infrared telescope, James Webb Telescope, is going to be discovering probably thousands of these objects within just the next few years. And so in the next year or so, we're going to be talking a lot more about this subject as new discoveries come in. And by the way, if you want to learn more about the telescope itself, check out some of the videos somewhere right there, if it's already out. And so looks like now we're going to be entering a new stage of astronomy, the stage where we're going to be able to see a lot of various planets and a lot of various planemos around us, and are going to most likely find some really incredible discoveries, with so many more rogue planets and various brown dwarf-like objects, very likely discovered not so far from planet Earth, and they were probably always there, but we just couldn't really see them. Only the infrared telescopes can usually detect them really well. And so once we find them, I'll make sure to follow this up with another video and explain exactly what we discovered. Until then, thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining the channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.